Hello everyone, very good evening to all of you. How are you all? So I hope every one of you is doing absolutely fantastic. So in our previous session we have finished GOC day 1. So like that was our first day challenge. So let me just give you a quick idea. How are we proceeding with this day 1, day 2, day 3 game? So guys, GOC day 1 was yesterday, where we have completed the introduction part of GOC, organic compounds, hydrocarbons, their classifications, their like degree of carbon and degree of unsaturation, right? So many things like what are aromatic, anti-aromatic, non-aromatic compounds. Then after that we have come to what did we study? I remember we studied IUPAC nomenclature. Yes. So IUPAC nomenclature we have already covered in very detailed way. Then right after IUPAC nomenclature, we also studied about the electronic effects. So today we have GOC day 2, and in second day of GOC, what are we gonna to cover? First thing, we will revise all electronic effects. We will understand the applications. So major applications of electronic effect is in the stability of reaction intermediate like carbocation, carbanion, carbon free radical reaction intermediates. After stability of reaction intermediate, we will also cover the acidic and basic strength. Among the organic compounds only. So like alcohol, water, then carboxylic acids, sulfonic acids. Comparing their acidic strength and basic strength, that will be covered in today's lecture. So this is your overview for GOC day 1 and day 2. Now I'll start. So let's start it from the GOC day 2. First of all, let us know what are electronic displacement effect. So displacement means there could be a partial or there could be a complete displacement of electron pair. This electron pair could be pi electrons, shared pair of electron. It could be a non-shared pair of electron also. So this electron pair is actually displaced from one position to another, creating polarity in the molecule, and sometimes this could be a permanent charge, sometimes it could be a temporary charge. These electronic effects are classified under two categories. One of them is called as temporary, another one is permanent. Temporary is the one that operates in the presence of some external reagent, external agent, external attacking reagent, right? And permanent effect is the one that is actually observed whenever whether any substance or any external reagent is present or not, it keeps on happening by itself. It's a permanent effect there. Permanent effects examples are given as inductive, mesomeric and hyperconjugation. And talking about the temporary effects, we have only electromeric effect with us. Then we have electromeric effect. Electromeric effect I taught you in the previous class also, that it's a temporary effect. It is observed in the presence of a reagent, and whenever a reagent approaches a molecule or a substrate which contains either carbon double bond carbon or carbon double bond oxygen, which is polarized, and because of the polarization the pi electrons are transferred, giving you the positive and negative charge. Now let me just explain one part to you. Positive electromeric effect is generally seen in the case of alkenes or alkynes, where a positively charged particle, which is actually called as an electrophile, an electrophile comes and approaches. Electrophile attacks on the negative charge density, but actually in chemistry the attack is always shown from the negative to positive. So this can also be shown like this, that here is a positive charge, here is a negative charge. So whoever is bearing the negative charge, that carbon will acquire this H positive, and its all valencies are now completed. Then it will be neutral, and here it will be having a negative charge. Not negative, it will be having a positive charge, and because of the positive charge only it is called as the electromeric effect, positive electromeric effect. We call it electromeric effect positive. Next example is negative electromeric effect. And what happens in negative electromeric effect? A compound such as carbonyl is being attacked by a nucleophile, where Nu is the nucleophile. The nucleophile attacks in such a way that the electron density shifts from one position to another, forming a compound where nucleophile is added with oxygen with negative charge. So since negative charge is appeared here, we call this effect as negative electromeric effect. It's very easy to explain, and I have already explained this part yesterday also in my GOC session 1. One of the question is here that if carbon double bond carbon is being attacked by X minus. So guys, as I told you, you can consider these two as positive and a negative, and since a minus charge species attacking, it will attack on the positive charge center, and this is how the product will look like. This creation of negative charge group is actually minus E effect. Very simple to understand. It is called as minus E effect. The correct answer should be what? C. Right? Absolutely right. Number 2 is called as inductive effect. We will simply take an idea and we'll simply revise this concept. We already have covered this part in our previous lecture. What happens in inductive effect? Inductive effect says that, let's say there is a carbon chain, and this carbon chain is actually connected with a halogen atom, and we all know that halogen being more electronegative, it attracts the electron density towards itself, especially the shared pair of electron goes a slide closer to chlorine, appears with a negative charge on chlorine and a positive charge on carbon. So now what will happen? Carbon is actually less electronegative. This polarization creates another positive charge on this substituent carbon, the nearest carbon. Since the electrons from here are shifted a bit toward this carbon, the same happens over here. These electrons are also shifted with a more lesser positive charge, and right after that it finishes. So we must know that inductive effect works up to 3 carbon atom only, and up to the 4th carbon atom it diminishes and it gets finished like that. So that is it. The electron pairs are shifted toward the more electronegative atom. It's a permanent effect, and it's a weak effect as shifting of electron is partial. There is no permanent charge which is appearing there. The partial charge was arising there. Inductive effect could be of 2 types. One of them is called as positive inductive effect, another is called as negative inductive effect. Positive one is the one in which electron donating group is there, and what we can say, just positive E effect, we are trying to give electron density to the carbon chain or the conjugated system, right? We are trying to give the, not conjugated system, simply the substrate system with carbon atom and the carbon chain. We are trying to give the energy to the carbon here, carbon chain. So these groups must be containing negative charge over them, or they could be neutral with electron pair with them, or they could be they must be having a complete valencies with their shared electron pair which can repel the electron density towards the chain. So CH2 minus is the one, NH minus, O minus, CO2 minus, CMe3. This CMe3 is actually 3 degree group connected there, then 2 degree, then 1 degree, and then 0 degree with methyl, then tritium, deuterium and hydrogen. Higher is the mass, higher is the inductive effect, and that is how we do. Then we have SiH3 over CH3, CH3, CH2D, like deuterium, number of deuterium, higher is the number of deuterium, higher will be the inductive effect. We can see it from here. So where is the deuterium? Higher is the number of deuteriums, higher will be the inductive effect, and lesser number of hydrogen is here, like that. Another comes minus I effect. So minus I effect does what? Basically, electron electrons are pulled from the carbon chain. Now carbon chain will be acquiring a positive charge because electron pairs are now pulled from the carbon chain towards the group. Now definitely the group which is connected to this carbon chain will be having either a positive charge or neutral with vacant orbital or some electronegative group with it, which can abstract the electron density towards it, especially the shared pair of electron. So this is some order that we have to learn it, and this is highly important order. This is very important for all of us, so we must remember the sequence in which they are given. Do remember the sequence in which they are given. Okay, now let us move forward from here. Well, this happens, Jaden, Michael. This sometimes happen because sometimes we are winding up the session. We were teaching there continuously for 4 hours or 3 hours, then sometimes we feel bored about that topic. Anyways, we have inductive effect, minus I effect, and I told you to remember this, basically the version and this particular what should I say, the sequence, because it is very important, and sometimes these things will be useful while we will be doing the relative comparison between the stabilities of carbocation, carbon ion, like that. Okay, take this idea. Inductive effect of chlorine is operating in, so inductive effect actually operates through the sigma bond pair, or we can simply say that through the complete carbon chain, and it's a distance dependent effect because we all know that after the fourth group the effect is completely neutralized, or it is almost zero. So we can see that, see, chlorine is here, this will give you partial negative charge, and this will be becoming partial positive. Then here also this will become partial negative, partial. Same applies here, partial positive, partial negative. It is applicable to all, right? One more question is here about the nature of this group. So guys, it is pretty clear. Okay, nitrogen, like carbon, deuterium, we all know nitrogen is quite more electronegative than carbon, and also with a positive charge it will try to attract the electron density. So what we can say that NH3 is a minus I group because it will abstract the electron density, the shared bond of pair, and itself will try to acquire the shared pair of electrons, so that the carbon connected with it will acquire a partial positive charge, and it will try to neutralize its positive charge with acquiring a partial negative charge. Deuterium, we all know, deuterium, hydrogen or tritium, all three comes under the category of positive I group. COO minus group, guys, try to check this out. CO minus, since it's a minus charge, and we can simply show this thing as it's a complete negative charge, so it will try to repel the electron density towards the system. It is increasing the electron density of the system, so it is a positive I group. But what about COOH? Does COH also do the same? So it is like a C double bond O OH. Now what you see, we do not have any negative charge present on the oxygen atom, and this is more electronegative. So it is more electronegative. It will create some sort of negative charge here and a positive charge over here, and then positive charge will try to abstract the electron density from the system, and it gives you as a minus I group. Now you compare it, minus I plus I plus I minus I, minus I plus I plus I minus I is option number 1 only. A is correct. Now the third electronic effect is called as resonance, and with resonance we study mesomeric effect, right? Resonance is a delocalization of pi electron from one conjugated system to another. Like how? Take this example, CH2 with a negative charge, CH double bond CH2. So we can see that this negative charge from this situation, from the given structure, can go like this, and only the pi electrons are shifted. The sigma bonds and the position of all atoms is exactly the same. So see, that is how it look like. So the only difference between these two is the placement of charge and the position of the pi bonds or pi electrons. So these are the pi electron, this is sigma, this is pi. One is sigma, first formed is sigma, another one is pi. So the relationship between these two are called as resonating structures. And I told you resonating structures are what? Unreal in nature. The actual structure doesn't look like this. The actual structure looks like this. CH2. We have a single bond CH. We also have a single bond here. There is a partial double bond, and this hole with a negative charge. This particular structure which I right now have formed is called as the resonance hybrid, and resonance hybrid is a real structure. Resonance hybrid is a real structure, and the energy difference between these two, is called as the resonance energy, RE. The resonance energy. So we are talking about a conjugated system. So guys, how does conjugation work? Like, how come I was very much confident doing this question? Like, how did I shifted minus charge from here and then I removed this? So conjugated system always looks like this, in this way, that some of the positive charge, negative charge, lone pair, fully filled electron, or vacant orbital, or a single electron, we call it free radical, will be in such a condition that will be separated by a sigma bond. Now take this example, pi alternate pi means double bond is there, then we have a single bond, and then we have a double bond. So this double bond can do what? This kind of transition can be done. See, so what will happen? There will come a positive charge, there will be a single bond, there will be a double bond, and there will come a negative charge. Are we guys understanding? Then we have pi alternative positive, so it's a pi bond, single, and then one carbon will be having positive charge. This can be done like this. So how does it look like? Positive charge over here, and then here a double bond. So double, single, double. Then we have pi alternate negative, double, single, negative. Then we have pi alternate odd electron, it's a free radical. Then we have pi one and then lone pair. Then we have double, lone pair, single, and now carbon the positive charge. Then we have lone pair and vacant orbital. Lone pair is here, and this is a vacant orbital. This is a fully filled lone pair, fully filled electron pair, lone pair. Then we have another question: in which of the following lone pair charge indicated, lone pair oblique charge indicated involved in resonance? Okay. So lone pair or the charge is involved in resonance. So see, double, single, double, single, double. So this goes like this. So this is yes. Yeah, we are having a resonance here. Then double, sorry, lone pair, single, double. So this will go like this. See how easy. So this is also resonance. Then we have double, single, and negative. Double, single, negative. Double will not like this. Instead, oppositely, it will work like this. So this is also resonance. So I guess the correct answer should be all. Next question: which of the following resonance will be possible? Okay, where is possibility of resonance? See, it's not a conjugated system. No conjugated system. We studied so many things about conjugation, but that doesn't match here. Here we have double bond which can be transferred here because carbon and oxygen is more electronegative. It will abstract its electron pair is like this. So this can move. And what will be its resonating structure? CH2C. Now this is having one lesser bond, so its valency is reduced. It will acquire a positive charge. Then we have CH double bond, CH single bond O minus. This is the resonating structure. Next is CH3COCH3. There is no resonance, no conjugation, no alternate pi bonds and anything. Then this also doesn't have because this is double, single, single. There is no two single bonds in line because they will be having a sp3 hybridized atom in between, and a sp3 hybridized atom kills the resonance because it's non-planar. It's not a planar atom and it cannot share the electron pair of pi electrons, p electrons, pure p. So correct answer should be B. Then we have stability of resonating structure. So let me write the points one by one, and what priority do we need to set will be given over here. So this is your priority order. Priority order to decide stability of resonating structures. So if we are given with the resonating structure, how are we gonna to decide the priority order? So let us check it. Priority order to decide the stability of resonating structure. Number one, neutral resonating structure is always more stable than the charged one. Number two, structure with more number of covalent bonds, and especially we are talking about the pi bonds only of conjugation, will be more stable. Right? Structure with more number of covalent bonds. 3. A structure with more number of complete octet atoms. like the atoms with their completed octet, that will be more stable structure. Number 4, what else could be the more stable? Next property comes that negative charge on more electronegative and positive charge on less electronegative atom is more stable. And the last and final fifth point, that which resonating structure will be more stable. Fifth point says that if a charge species is there, so same charges should be as distant as apart, should be as distant as and opposite charges should be closer. Is it clear, everyone? These 5 points. Try reading all the points once. In the priority, first priority is to check whether neutral or charged species are given. So neutral will always be more stable. Number 2, the species which contains more number of bonds. If we are talking about covalent bond, we are talking about the pi bonds, because sigma bonds will be remaining same sigma bonds, and the number of bonds and the positions are always same for the atoms, especially in resonance. The only thing which changes in resonance is the position of pi bond, delocalized system from one to another. Third is structure will more number of structure with more number of complete octet. So wherever you will be finding more number of octet completed there, that structure will be more stable. Then negative charge on more electronegative and positive charge on less electronegative atom is more stable. So this is also we have to take into account that negative charge is there on more electronegative, like that, and same charges should be kept distant apart, and opposite charges should be closer, so that stability will be more. Now try this question and please give me the answer using this priority order of the properties. Now try giving me this answer. Kushagra is saying that I am feeling sleepy. Let it be, yaar. We should be very much selfish by this time when we are having our exam just a month later. So this time we should focus upon what Sanjay sir is teaching, what is written on the board, how we should approach to the question, rather than ki is sir sleeping or sir sleepy or what. Not like that. The least stable canonical we have to tell. So what will happen here? Actually, what do we see? We have, first of all, this one is non-charged. This is most stable structure. This is most stable. Now we have to compare these two structure. So these both have same number of bonds, same type of charge is there, complete octet are also there. Complete octet of all atoms, and second, so oxygen with positive charge versus nitrogen with positive charge, oxygen positive charge versus this. So this is more stable. Oxygen with positive charge is less stable because oxygen is actually more electronegative, and this nitrogen is less electronegative. The correct answer will be O positive. So this is the least stable. B. Bill, correct. Nithila SRS submitted with the correct answer. Very good, Nithila. Then we have resonance energy. As I told you, resonance energy. Okay, keep resonance energy always negative. The difference between the resonance hybrid, the energy of resonance hybrid versus the energy of the most stable resonating structure. So that difference should be in negative. That is in negative. Okay, this amount of energy is actually produced. So it is again. So that is a different thing which we are having here, and this is a like theoretical value of heat of hydrogenation for an alkene. So benzene has theoretically heat of hydrogenation is 87, and experimentally the value is found to be 51. So the difference between these will be because of the resonance energy. So resonance energy is actually equals to we can take this as negative also, that 87 51 minus 87, so negative of can be the correct answer. Now we have come to the positive M effect or mesomeric effect. So what is mesomeric effect? Just like the resonance, some group is there which is either providing you the electrons or abstracting the electrons from the system, creating a positive or negative charge respectively. Then in that way, plus M effect works in the form of resonance, and there could be certain groups over there. The one group is OMe. So guys, take this example. This particular group till here is a conjugate system. This is a conjugate system. Conjugate system, in this conjugate system, lone pair is donated in such a way, and it is reshifted and it has become like this. So see, substrate is now provided with the negative charge. So basically electron density is gained. Your electrons are gained actually, gained by substrate. So whenever a substrate gains electron from some group, it is called as the positive M group. And these are some example like halogen, OH, OR minus. This is the order of positive M group that we have to learn, and I'm star marking it because it is very important. And very first should be the carbon with minus charge, that is CH. This is CH2 minus, CH3 minus, C minus, and then we have NH minus, then OH minus, right. Then O minus, NH2, NHR, and R2. Just learn this order. This is very important order as far as the concern of M effect, which is called as the mesomeric effect. Okay, try this. Sure. I'll explain. Cross and extended, I'll explain. Next we have negative mesomeric effect. Negative mesomeric effect is, it is the effect in which a group is pulled the pi electrons from the system. The system will definitely be acquiring a positive charge, or electron density will be removed from the system towards the group. So electron withdrawing group is actually this electron withdrawing group in conjugation is called as the deactivating group. These are some set of examples, and for example we need to understand this example. Take it. So this is right now our conjugated system, which is attached with a nitro group. conjugated system is attached with a nitro group. So what will happen? Oxygen is more electronegative. This will basically pull the electron density from nitrogen, oxygen, and this is the pi electron density that gets converted into negative charge. So this is the negative charge, and then this has to come in this way in order to basically counterbalance the valency of nitrogen, and then this carbon will require a positive charge. Right, positive charge. Definitely it will be acquiring a positive charge because electron withdrawing group is attached there. So strongly deactivating group will be there. This is something that we have to learn. Moderately deactivating groups are there. Strongly deactivating groups are there. Cyanide and nitro. This order, please learn this order. Okay, this is very important order. So nitro, cyanide will have the highest extent of negative M effect, followed by nitro. So cyanide has the highest, followed by the nitro, and then we have the same CHO, then we have COR, then we have COCl, etc., and then the rest is the order here. Try this. Hyperconjugation. We have hyperconjugation. So what is hyperconjugation? It's a special type of resonance. A special type of resonance. What happens in special type of resonance? It happens with sigma pi conjugation. It is also called a sigma pi conjugation. And why is it so? Because guys, where does it operate? By the way, first of all, we must know it actually operates wherever there is a alpha hydrogen with respect to a conjugate system, a conjugated system of alkene, alkyne, carbocation, free radical, etc. So there actually it works. Okay, it could be benzene also. So how is it working? Take this example. CH, 2H and CH3, not CH3, CH2 with a positive charge. Now try to understand this part, guys. This is actually a carbocation. So now in this carbocation is there, and it makes carbon with positive charge is making hydrogen next to its the carbon to its next carbon, which is called as alpha carbon, as an acidic hydrogen. So since it becomes an acidic hydrogen, it will try to release H as H positive, and its electron density will be shifted like this. So what you will see are resonating structures. The similar symbol will be used as a resonating structure, and it will become a CH2 double bond CH2. It's an alkene now. And what about the H positive? H positive will keep on roaming around the pi electron density. So this is called as a conjugate. We call this structure as a hyperconjugating structure. Hyperconjugating structure. Right. The another example can be seen. Okay, free radical will also be having the similar kind of thing. Like this is a free radical, and this is connected to a carbon, and then it is a hydrogen. We all know one hydrogen is formed of two electrons. One bond is formed of one covalent bond is formed of two electrons. So what it will do? It will like go like this, and this will come up like this, and hydrogen departs there. Not a full sign, a half. So this is how it look like. Similar to the, exactly similar as the, what should I call it? Exactly same as the carbocation, right? So initially we studied hyperconjugation free in carbocation, then we studied in free radical. Then third could be hyperconjugation in alkenes. So what happens in alkenes? Take this example, CH2-1H, single bond CH, double bond CH2. So now this is doubly bonded carbon. So next carbon to the doubly bond is called as alpha carbon. Then again the conjugation can be there. Hydrogen becomes acidic, loses its electron pair over here, and this electron density is shifted like this. So how does it look like? It's a resonating structure, or kind of its conjugating structure. Another structure will look like CH2 double bond, CH single bond, CH2. What did we do? There will be a minus charge, and this positive charge H will also roam around here. Next, so guys, this will be highly helpful in deciding the the stability of carbocation, carbanion, free radical. In this way, hyperconjugation is very important, and not just hyperconjugation. All the electronic effects will be showing their applications accordingly. Now you try this question. Most stable carbocation. Okay, there is one more point I forgot to tell you. This point is called as the number of hyperconjugating structures. Number of hyperconjugating structures. Right? So guys, this is a number of alpha hydrogen plus 1. 1 is the original molecule given to us, and number of alpha hydrogen is the number of possible hyperconjugating structure. Okay? Like this. Plus 1 we are taking also. Okay. So this plus 1, the structure is the original molecule, and it doesn't have sigma electron density of carbon hydrogen bond. some questions. Let us solve some questions. Most stable carbocation among the following is, what do you think? Which one of them is more stable? So guys, in these way, first is the inductive. We all know two-sided effect is working, that is inductive. But no, we must know the priority order also from here. That if we have to see the priority of electronic effects, because we have studied resonance, we have studied hyperconjugation, we have studied inductive. So out of these, which one is more dominant? The priority says that resonance oblique meso comes on top because there is a permanent transfer of the electron. Then comes the hyperconjugation, but here only carbon hydrogen bond or hydrogen bond is only departed. So hyperconjugation, and then we at the last it comes with inductive, because in inductive only partial charges are appeared. So no need to write down the inductive here. This is the order we have to follow. So like an example, take this example. Let's say this is the example. It's a carbocation and another carbocation is this. Now you got to tell me which one of these carbocation is more stable. Come on everyone, comment me which of them do you find is more stable. Let us say this is first, this one is second. So out of first and second, the more stable carbocation will be what? You take your time, just allow me a 1 minute. I'll quickly go and bring some water for me. I'm feeling a bit dehydrated. Just allow me a moment and you try. You try which one of them is more stable. The question is already been asked. More stable. Try it. Yes, so I'm back. So I asked you this question, everyone. Let's see who has submitted me the correct answer. First is more stable. Somebody said first is more stable. Yeah, okay. So actually, we are wrong here, everyone. Not we, actually, you are wrong, my buddy. First is not stable. The more stable is this. If we talk about plus I effect, the plus I effect is seen more in first inductive. But if we talk about the plus H effect or plus hyper, whatever the hyperconjugation we study here, in which the electron density is provided to the system, these all are under the part of positive hyperconjugation. Similarly, there is one more thing called as negative hyperconjugation. In negative hyperconjugation, what happens? In negative hyperconjugation, electron density is pulled from there. But negative hyperconjugation is not in our syllabus. We usually study positive H only, and that also in the case of hydrogen. So now what we'll do, alpha hydrogen, in terms of alpha hydrogen, number of alpha hydrogens are more in how much? Alpha hydrogen will decide the hyperconjugation. So plus hyperconjugation is higher in what? This has 0 alpha hydrogen. Alpha hydrogens are 0 here, and alpha hydrogens are 3 here. So this will give you 3 basically hyperconjugable structures with one original structure. Total 4 structure will be there, called as hyperconjugating structure only, right? So plus hyperconjugation is in first, is in second. So second is more stable. So that was a very beautiful questions we had, and probably you all have gone through it. Maybe you all have understood the concept as well. हाँ, कहाँ हो तुम? So that was the logic behind this question, and now we'll move forward. I actually forgot the pen somewhere and I'm finding it, and that is why I'm okay, there it is. So moving to the next part, somebody that time asked me what is the difference of extended versus cross conjugation. So not a very huge topic, very simple one. So I'll explain you extended versus cross conjugation. So let us find a system like this, extended. So let us say this is your extended system. And here is a positive charge. This is extended system. And cross could be this. So what is happening here? Guys, we all know that we can see that this is how it look like. The double bond has changed its position like this. So even if we draw these two are the resonating structures. If you draw the resonance hybrid, how does it look like? Not required, we'll simply solve it. Now try to take this thing into account. So this can give you either this or either this. So although the both of them will be having resonating structure as the same, only one of the resonating structure is absolutely the same, but the difference is only this pi electron shifted over here, and these two are basically fighting to each other. In cross conjugation, two resonance are fighting towards each other. That is why one takes place at one time. What we can see, one conjugation takes place at one time, and due to which what will happen, the positive charge, or we can say the charge distribution, is limited, whereas coming over here, what do we see? That complete conjugation is happening here, and in extended conjugation, charge of pi electrons are completely distributed up to longer extent, up to longer basically distance, and since longer distance it is basically distributed, it will give it more or less stability. It will give it more stability rather than the cross conjugation, because in cross conjugation only this double bond will participate at once. So although the structure looks like this, but this positive charge is shifted from this to this. Only in this positive charge is actually distributed into this. Like if you draw the resonance hybrid, how does it look like? This didn't even move. This is here and here. So this double bond is partial double bond here, with a positive charge distributed within 3 atoms only. This is its resonance hybrid. Because why is it the resonance hybrid? Because sir, only one electron pair or one pi bond will participate at once while going for the conjugation. But here we can see the resonance hybrid also shows us that the charge is distributed throughout the system, and like this positive charge is distributed on the complete molecule. This is resonance hybrid. This is more stable. This resonance hybrid is less stable. Is the concept of cross versus extended clear to everyone? Now I'm sitting in a side. Is the concept of cross versus extended conjugation clear to all of you? So cross conjugation basically restricts the space for a particular charge or the pi electron density, but in extended we have the plenty of space to move through and where we can distribute the charge, and that is why charge, higher is the distribution of charge, higher is the stability, lesser is the distribution of charge, lesser is the stability. Now we will move forward and then we'll start solving some more questions, Most stable carbocation among them is what? Anyways, we'll come to it today and we'll solve more questions on carbocation and its stability, carbon ion stability, like that. Here we need to simply calculate out the number of alpha hydrogen. This is alpha, this is also alpha. 3 is here. Now this is alpha, this is alpha. Number of alpha hydrogen will be 4. This is how many alpha hydrogens are here? 3 here, 2 here, 5. Then alpha hydrogen over here. This is only alpha, and that carbon will become beta. So alpha is actually 2. Now check out how many number of alpha hydrogens are there. Higher is the number of alpha hydrogen, higher is the number of hyperconjugating structure, and higher is the distribution of charge. So C is the correct answer. Another question, which of the following which of the following alkenes hyperconjugation is not possible? So hyperconjugation occurs because of the alpha hydrogen. So this is alpha, this is also alpha, this is alpha, this is alpha, and total number of alpha hydrogen will be how many? This has 2 bonds, means 2 hydrogens will be there, 2 plus 2 and 3 plus 3. So this will become 10. Here if we talk about, this is your alpha, this one is also alpha. So alpha hydrogens are how many? 4. Talking to this is have alpha hydrogen equals to 0 because there is no alpha carbon. This is alpha, this is also alpha, so alpha hydrogen will be 6. The correct answer will be C. If anyone faces any doubts, do let me know in the comment section. I'll respond to you guys. Keep on liking the session, everyone. Next is this question, stability of the alkene. So alkene stability can be decided using number of alpha hydrogens. So where can you find the alpha? This is doubly bonded carbon, the next carbon to it is alpha, the next carbon to it is alpha. So total number of alpha hydrogens over here are how many? 2 plus 1, 3. Now alpha carbon is this is also alpha, this is also alpha. So alpha hydrogens are how many? 3 plus 2, 5 plus 2, 7. Now here alpha hydrogens are how many? This is also alpha, this is also alpha. 2 plus 2, 4. So now tell me which one is most stable. Most stable is the second, least stable is the third. So second, third, first, second, third, first, second, third, first, A. Very easy. Finally, now we have come to the breaking of bonds, and we'll understand the breaking of bonds, and then we'll come to another important part called as reaction intermediate and their stabilities. This is one of the application of the electronic effect, like how can we compare the stabilities of these reaction intermediate, carbocation, carbon ion and carbon free radical. So there could be 2 type of ways of bond fission. Bond fission means breakage of bond, and we also call it bond cleavage. So let us suppose we have a compound AB and there is a, let's say, high electronegativity difference between A and B. So if there is a high electronegativity difference, then if you're trying to break this bond, this bond breaks in such a way that it gives you A positive and B negative, and that is also that, let's say B is more electronegative, this is more electronegative, and let's say A is less electronegative. So the total electrons will be A positive and B minus. Because of the high difference of electronegativity, this breaks like this. Now take another example where A and B are with similar electronegativity. There is a very less electronegativity difference. Delta is very low. So what will happen here if we break down this bond? It will give you A free radical plus B free radical. What is the meaning of radical here? The meaning of radical is, see, there are 2 electrons. So one electron goes to this, one electron goes to this. This is called as the homolytic bond fission. This is called as heterolytic bond fission, and this one is called as homolytic bond fission. So guys, we must know that because of the homolytic bond fission, we get free radicals. What we get is the free radicals, and because of this we can get carbocation or carbanion. Carbocation and carbanion. Now try solving this question. A compound which undergoes homolytic bond cleavage, there is a compound that undergoes homolytic bond cleavage, will lead to form which of the following species? Cation, anion, free radical. Yes, only free radical. Very easy questions, very easy answer. We have another question. No, we don't have any question now. So we'll discuss something about carbocation first. So what is a carbocation? How does it look like? Or let me just give you the idea of all of these three at once. So here is carbocation, we have a carbanion, and we have a carbon free radical. So I will give you the idea of their structures, what groups can basically stabilize them, like that. Okay, for all we'll study one by one. What should we study first? Let's say carbocation. So take carbocation. So carbon with 3 bonds, 1 positive charge and 1 vacant orbital, right? This is your vacant pure p orbital, and these 3 are what? These 3 would be the planar bond. These 3 are in the same plane. Like this. This is the structure of carbocation. So basically a carbocation, what we can see is a 6 electron species. 6 electron species. It is electron deficient in nature. This is electron deficient in nature, and since this is electron deficient in nature, it is stabilized by electron donating group or electron releasing group. Whoever donates the electron density to it, it is stabilized by that. Rest, we all know, because of the 3 bond, its hybridization is sp2 and its geometry will become trigonal planar. Its geometry will become trigonal planar. Now, rest of the properties we'll discuss in the next page. Everything is given over here, like how is it formed, heterolytic cleavage, octet is incomplete, complete, that we'll study there. Okay, I'm just giving an idea, how does it appear, how does it look like. Okay, that is what we are doing. Now let us talk about carbanion here. Carbanion, carbon with a negative charge. So definitely a carbon with a negative charge will be having one lone pair with it that has 2 electrons in it with a minus charge, and 3 bonds will be here, 1 bond, 2 bond, and another bond. So this is how it look like. How many electrons are there? 1, 2, 3, 4, 5, 6 and 7, 8. It's a 8 electron species. Since its octet is complete, it is actually electron rich in nature. If it is electron rich, it will be stabilized by, its negative charge has to be accepted by someone. So it is stabilized by electron withdrawing group. It is stabilized by electron withdrawing group. Then if we talk about the hybridization, hybridization is sp3. Geometry is tetrahedral. And its shape, geometry is tetrahedral and its shape will be, what is it? Pyramidal. So trigonal pyramidal. So that is it about the carb anion. I hope this part is absolutely clear to all of us. And even if not, we'll come to more properties in next page and we'll discuss all those properties. Then we have carbon free radical. What we have is carbon free radical also. Give me a sec. चलो बढ़ते हैं आगे। तो तीसरा जो होता है दोस्तों वो है अपना कार्बन फ्री रेडिकल। तो भाई फ्री रेडिकल तो काफी फ्री रहता है। तो देखो इसमें इसका हाइब्रिडाइजेशन भी sp2 ही है वैसे। तो इसमें भी कुछ ऐसा दिखाई देगा ये कि यहाँ पे प्योर वाइटल, लेकिन इसमें एक इलेक्ट्रॉन है अनपेड इलेक्ट्रॉन। देखो यहाँ पे ये जो है ना क्या है, 1 अनपेड इलेक्ट्रॉन। हियर इज 1 अनपेड इलेक्ट्रॉन। यहाँ पे कितने इलेक्ट्रॉन्स इन्वॉल्व है टोटल मिला के? 1 2 3 4 5 6 और ये एक 7 हो गया, तो 7 इलेक्ट्रॉन स्पीशी है। अगर 7 इलेक्ट्रॉन की स्पीशी है दोस्तों, तो ये इलेक्ट्रॉन ऑक्टेट तो इनकम्प्लीट हो गया, तो इलेक्ट्रॉन डेफिशिएंट हो गई। तो इसकी प्रॉपर्टी सेम वहीं से मैच हो जाएंगी, डेफिशिएंट रहेगा। अगर इलेक्ट्रॉन डेफिशिएंट है तो किससे स्टेबलाइज होएगा? इलेक्ट्रॉन रिलीजिंग ग्रुप या इलेक्ट्रॉन डोनेटिंग ग्रुप से। ईआरजी और ईडीजी एक ही होते हैं ना, ईआरजी कहो या ईडीजी कहो एक ही बात है, घबराना नहीं है। Yeah, so then we have talking about its hybridization. Hybridization will be sp2. Geometry will be none other than What will be the geometry of this compound? Geometry should be the same only, trigonal, planar, and what else is there? Hybridization. So as already covered, geometry is okay. Every point is covered till here. So that is how we compare these three type of. These are the three types of reaction intermediate. Then next is here so now try reading all these properties, everyone. You please better read out all these properties. So read out all these properties. What are the properties? Their formation, their number of electrons they carry, incomplete, electron rich, deficient, electron leaching. Then we also have one more property, unpaired electron. This is 0 unpaired electrons are there, 0 unpaired electrons are there, 1 electron pair is this. So what do we see if we talk about the magnetic behavior? Carbocations will be diamagnetic in nature. This will also be diamagnetic in nature, no unpaired electron, and this will become paramagnetic in nature because of the presence of 1 electron. Sorry. Now we'll start solving some questions on the properties we studied. Arrange the carbon ion. We need to arrange these carbon ions in the order of decreasing stability, decreasing order of their stability. So how do we do it? Okay, see, this group is actually doing what? Plus I. So basically this is disturbing because a carbon ion will be stabilized by the. When can a carbon ion be stabilized? A carbon ion is usually stabilized by electron withdrawing group, but these three CH3 group will provide it positive I effect. So that's why, because of the positive I effect, yeah. So we were discussing the part that this is minus I. This Actually, chlorine has a vacant orbital, right? So vacant orbital, single negative charge. It's a conjugation, and also because of 3, especially 3, so minus I or minus I plus resonance. So minus I is also there, resonance is also working. So because of that, this negative charge is even more stable. Here also what we can see is there will be a plus I, but smaller plus I than this one. This will be having higher plus I because of 3 methyl group. Here only 2 methyl groups are there, 1 hydrogen. Little bit smaller will be here. Here also we have benzene ring with us. So benzene ring will definitely undergo conjugation, and this negative charge will be distributed. So only thing that we can see over here is resonance. And also, since this carbon is sp2, this is sp3, sp2 carbon has more electronegativity, so small quantity of minus I will also be working. I think correct answer should be Cl3C minus should be the most stable, and then this order should be followed. I think B should be the correct answer. So I would like to check what you guys opt, what you guys think of this, but my correct option or opinion should be option number B. I will go for B. B is correct. Another good question is here. So we see that hyperconjugation will work, and number of alpha hydrogens are how many? 3 plus 3, 6, because these two are alpha. Here 1 alpha, 2 alpha, 3 alpha, alpha hydrogens are 9. Then here also carbon with positive charge, and that too sp hybridized carbon is here. So this will be highly unstable. A doubly bonded carbon with a positive charge is highly unstable. And what should I say? In this, at least hyperconjugation may work because of this. Plus I and plus H also may work, but here I don't think this will work. So I think only plus I may work because of this, but I don't think this will work up to a larger extent. So the correct answer should be C. 3 will be the most stable, followed by first. So 3 first, and out of these two, I think this one is lesser stable. So 4th is the least stable actually. This is the least stable. So 4, I think C should be the correct answer. Now let me check it. Oh, C is perfect. So whatever we are planning, what we are thinking, we are going in a very good direction, and that is what I want every one of you to attempt with. So guys, we have another carbocation we have to study in detail now. Carbocation or carbonium. So we already have gone through the structure of carbonium. You all know the structure of carbonium. How does it look like? It's hybridization and everything. So carbon has a hybridization of 1s to 2s to 2p2. In its excited state, it will this s electron goes over here. 3 electrons will come into this. 1 electron is here. 3 participate in hybridization. So let me just show you. Is it the next page? Yeah, it is in the next page. So I don't need to show you, directly I'll explain. So 1 electron goes here, 1 electron goes here, or all 4 orbitals with similar spin of the electron. 3 of them undergo this, 3 of them undergo hybridization, intermixing, and they will go 1s and 2p, so it will become sp2 hybridized, and this 1 remains with pure p orbital. This is pure p orbital. So carbon is sp2 hybridized, and this is, we already have covered this part. Since it is electron deficient, it works as a electrophile, because something which loves electrons or something which want to accept electrons is called as an electrophile. So it works as an electrophile. Then we have types of carbocation. How many types of carbocations are there? So carbocation could be saturated, unsaturated, not saturated, but still benzylic carbocation, vinylic carbocation, So many types of carbocation exist, so we'll try to understand every one of them. Number one is carbon with a positive charge like this, very simple one. You believe me, their hybridizations also changes, so I'll allow you to know about the hybridization. If you talk about the hybridization here, so this is actually sp2. Then primary, secondary, all of them have the same. Primary and secondary both have hybridizations sp2. Primary means which is connected to one carbon atom. Secondary means which is connected to two carbon atoms. Tertiary is connected to three carbon atoms. Again, the hybridization will be sp2. We have allylic carbocation. We have allylic. Again, the hybridization is sp2. Then we have benzylic. What we have is benzylic carbocation. So in benzylic carbocation, benzylic means the carbon next to the benzene ring, and it's more stable because of the resonance stabilized, right? So because of the resonance stability, this carbon is highly stable. Again, the hybridization will be sp2. You might be wondering, why am I giving you sp2 hybridization if it's already, because all of them might be having the sp2, but it's not like that. I'll come to that and I'll explain you like how hybridization may change. Vinyl means a double bond containing carbon. Allylic means double bond, next carbon to that will be having positive charge. So vinylic, we can see vinylic, it is also, the hybridization will become sp2 here. Even in aryl is the one which is benzene ring. So in benzene ring, if it is a positive charge, we can count total electron sp, but this is not sp. This is also not sp hybridized. No, not sp hybrid. Don't consider that that this carbon will be sp. No, maybe there are two total steric number we can see. 2 sigma bonds are there. It can be called as sp, but guys, one vacant orbital is empty over here. I must draw this. This is your vacant sp2 hybrid orbital. So again, the hybridization is sp2. Next we have, how many did we discuss? 8. Ninth, guys, ninth is actually, let me check if it allyl was given or not. Okay, allylic is already covered. Allylic means next to the double bond. So another one, very important example, not. So if we talk about these two, versus let's say if we are talking about these two carbocation, and somebody asks us that what will be the hybridization of these two. So hybridization of carbon which is bearing the positive charge there, the hybridization is sp2 there. The hybridization over here will be sp. The hybridization here cannot be sp because sp hybridization requires a linear geometry, but here it is linear, and that is why it may have. So what does it have, by the way? It has a vacant sp orbital, and one is forming the bond here, sigma bond. Here also, guys, what you'll observe is, here also you will have a vacant sp2 hybrid orbital. So that is what these structures are. There's a note I made it in order to explain you the hybridization. Next we have stability of carbocation. So stability can be very much easily explained. Electronic effects, we all must know that the priority order will be positive M, always more dominant over positive M over positive R, both are the same, nearly same. Resonance or mesomeric effect, then we have positive H, and then comes at end the positive I. This is the order of electronic effect, electron releasing group or electron donating group. So hyperconjugation is seen already, we have covered this part. I'll move forward directly. Resonance is already covered, typical cases are also covered, I have already explained it. Vinyl, I think I have already covered it. Okay, vinyl has sp. Yeah, it may have sp because one is forming the bond, another one is also forming the bond with hydrogen, and there is one, not one, in fact two. Vacant orbitals, vacant p orbitals. We have another good example here. Acyl carbocation is something, acylinium carbocation we call it. So acyl group is R C double bond O, where C is possessing the positive charge. But here, what do we see, that carbon is forming only 3 bonds. So we can say that carbon has incomplete octet, right? You all remember this is the resonating structure. If carbon has the incomplete octet, but if we move down, no yaar, why is it stable? sp hybridized carbon in conjugation with lone pair. sp hybridized carbon in conjugation. Okay, it is in the lone pair. Okay, good. So this is acyl carbocation is actually stable, and this is not correctly mentioned here. This should go like this. It should come up like this, and then it will be a triple bond. So that is what I am explaining you, that because of the triple bond, this has incomplete octet, and this has a complete octet, and because of the complete octet, this is major, this exists more, this is more stable, this is lesser stable. The stability of carbocation is measured in terms of heat of formation. Since it involves the breaking of a bond, it is a endothermic process. Further, more is the delta HF, lesser is this. Okay, it's okay. So guys, this is the general order of carbocation, the general order of the stabilities of carbocation that we have to learn. So which of them is more stable, which of them is not, just take this idea. Troponium carbocation has higher number of this has 7 resonating structures, that is why it is more stable. This can have 3 resonating structures, highly stable one. Then we have 9 alpha hydrogens are here. So 9 alpha hydrogen is a big reason for stability of this compound. this carbocation. Then we have resonance stability here. This is called as phenyl, not phenyl, this is called as benzyl carbocation, which is resonance stable. So everything can be explained. Why can't we explain this? What is the logic behind its stability? CPM, we call it cyclopropyl methyl carbocation. Anyways, I'll explain it. It's very important. Rest is the stability, very much explained. This is your alpha hydrogens are getting reduced, as you can count, 6. Then this is your resonance stabilized. Conjugation is there. We have 3 alpha hydrogen here, so it is like 3 degrees more stable, followed by benzylic, then 2 degree, then we have 1 degree here, then we have 0 degree somewhere, right? Even this is more stable than this. CH3 plus is also more stable than these two. These are highly unstable. Doubly bonded with a positive charge or phenyl with a positive charge are very highly unstable. Hybridizations are sp, and this is sp2. So what about the dancing resonance? Let us try this this part, cyclomethyl propyl carbocation. What is with CPM? We call it cyclopropyl methyl carbocation. So what is the specialty of this carbocation? What is CPM and why is it so popular? So guys, its structure somehow look like this. So there is a bond, there is a sigma bond, there is a sigma bond between the hybrid orbitals of carbon, right? And then this is a sp3 hybridized carbon atom here, sp3, and there occurs this CH2 group with a positive charge. So this CH2 group with a positive charge has a empty orbital here. This is your empty p orbital. This is your empty p orbital, pure p orbital. So because of this tetrahedral carbon, this vacant orbital comes closer to this, where this type of conjugation occurs. This type of conjugation occurs where the sigma electrons, these are the sigma bond, and this is p orbital. Sigma p conjugation occurs. Sigma p conjugation occurs. So sigma electrons are there, and this is the p orbital, which is like a empty orbital. So electron density is shifted into such a direction. This becomes a sigma pi resonance or sigma p resonance. So this type of conjugation is also called as dancing resonance. Also called as dancing resonance. So let's dance, everyone. Let's dance on this dancing resonance. So this is the beauty of dancing resonance, and this makes CPM, cyclopropyl methyl carbocation, as the most stable out of all the categories, even more than benzylic, even more than 9 alpha hydrogen containing tertiary butyl carbocation, even if it is more stable than any of the existing carbocation. Yeah, more stable could be those in which more number of this CPM will be connected. So like this is an example. Drawings are very bad. See, this is more stable than the one which is having two and then having a 1. like that. Now tell me who doesn't understand this part. Whoever doesn't understand, do let me know. I'll re-explain this part. Not a problem. Now I think we should start solving some questions. There we go. First question, write the correct order of stability among the following carbocations. Out of these carbocations, we got to give them the stability order. Very easy to decide. Anyways, what is the factor working here? Resonance is here. Here is also two types of resonance. Cross resonance might be here. So this is also resonance plus how many number of alpha hydrogens are there? This is CH3, 3. Here resonance plus number of alpha hydrogens are how many? This is alpha, 6. Here alpha hydrogens are how many? 1, 2, 3, 9. So third should be the most stable, I guess, because what do we see? More number of benzene are there. See, there is it could have been an extended conjugation also. This might be cross conjugation, but still there are more number of possibilities available for conjugation than this compound. This compound could have been somewhere like this, where extended conjugation could have seen. So my answer will be, since there are two benzenes which are stabilizing a compound, 3 is most stable. Now alpha 9 is actually very stable compound, but only in that condition where simple benzene with a positive charge is given, benzylic carbocation. But since benzylic carbocation has 6 alpha hydrogen, first will be chosen here and then it will become second. This is the order of stability. All set, all clear? Why not? So tomorrow I'll take a long shot on like the same only. GOC day 3 will be dedicated to isomerism. So today we had 2 tasks. One is the just revising the electronic effect, then taking the applications. But the application of electronic effect is huge. Like first is the stability of these intermediates. Till now we have covered carbocation, then we'll cover carbanion, then we'll cover carbon free radical, then we'll also understand the what do we call it? Carbocations rearrangement in carbocation is another important topic, and then we'll come to acidic and basic strength also. So huge part. So lots of scope here. Then we have decreasing order of the stability of following cation is. We have 4 cations here. Decreasing order has to be like known. See, this part is pretty much clear. So everyone knows that resonance will happen. Now everything depends upon these groups connected over here, which will provide them mesomeric effect. Now let us check what is their nature. This OH will definitely be providing this is having positive hydrogen plus H, this is having plus M less than minus I. Inductive effect is more dominant for halogens, always remember that part. Plus H is always dominant over positive I. Here also positive M greater than minus I and lesser, a bit lesser plus M then minus I. So correct answer should be most stable is Q, then P, then R, and the last will be S. Do we have any option as such? QPSR, QPRS, QPRS, D is the correct answer. Perfect. Next question, the same thing has to be applied. What is the nature of this compound? This particular OH group is a plus M group. Plus M, but it also does minus I, but minus I doesn't dominate. We have nothing over here. This group has a both side effect. Okay, this is called as a cross conjugation. This is cross, this is doing cross, and because of its cross conjugation, its contribution cross conjugation, and that is why it is and also it is not that much plus M group, so small plus M will be written down over here, then minus I, and then last one has literally minus M effect, because this is how it withdraws electron density, or minus I is also, but dominant part will be minus M. So S is the most unstable and P is the one most stable. So P is the most stable and S is the most unstable. I think A should be the correct answer. And then we have R and then Q. Is this clear all to every one of you? Is this clear to every one of you? This was a good question, by the way. It was a very good question, by the way. Now we have come to carb anion. Next one is called as carb anion. What is carb anion? So guys, whenever a carbon chain is connected, to a metal atom, like alkyl lithium, alkyl sodium, or Grignard reagent, so they contain carb anion in them. You know, whenever it is removed, electron density will go to the more electronegative. This carbon is more electronegative. And metals are always what? Less electronegative or more electropositive. So they will not accept the electron pair. They will acquire a positive charge. This will acquire a negative charge. So these are the short-lived species with reactive intermediate species carrying 8 electrons in valence shell. Zup, zup, zup. These all things which we have already covered. The only uncovered part is about that it behaves as a nucleophile. It has a pyramidal geometry and behaves as a Lewis base because it can donate an electron pair. Now we have to think that how can we stabilize it. So electron, always remember that stability will be decided by electron withdraw. Stability of carbon is directly proportional to the presence of electron withdrawing group, because the negative charge has to be distributed so that it will become more stable. Again, minus M oblique minus R group will stabilize the most, followed by minus hyperconjugation and followed by minus I. So minus hyperconjugation is not in our syllabus, so only these two will operate, minus M and minus I. I'll write down not in our syllabus. कोई भी डाउट हो पूछ लेना. Inductive effect. Then we have inductive effect. So inductive effect, no doubt, minus I stabilizes, plus I destabilizes. Resonance, we all know resonance and the working of resonance. CH2 minus negative charge is shifted here and it stabilizes it. But so increasing stability of carbocation is like higher is the number of methyl group, higher is the inductive effect and higher is the plus H effect also, and that is more stable. A tertiary carbocation is more stable than tertiary carbanion. Carbanion tertiary is highly unstable. This is opposite order. Both of them are showing opposite order towards their stability with the presence of these group. I think that's it. Now we'll solve some questions. The question says that write the correct order of the stability of the following carbon ion. So this is the carbon ion, and we have nothing over here, just a simple plus I, so it's not required. But again, one thing is there. This is everyone sp3 hybridized, this is sp2 hybridized, and this is sp And we must know that electronegativity is directly proportional to percentage S character of the hybridization. So what do we see? That electronegativity will follow the order of what is it? sp3, sp2 and then sp. And higher is the electronegativity, more is the stability of the negative charge. So stability will also become what? A, B, C. I think this part is pretty much clear to all of you. Very much clear to all of you. Next question. Okay, you better try this question by your own. Stop asking me to solve all the questions. Please try the efforts by your own. Well, that will be very much helpful. And I'm standing here. You may ask your doubt, any doubt, whatever you are facing in the chat box only. But do let me know. So the arrangement is shown like this, and when it is attached to a benzene unsaturated group in increasing or donating will tendency will what? For donating, it's an electron donating species tendency. So guys, I told you it is saying that benzene, if it is connected to this system like CH3 and CH3. Okay, but basically one more thing is here to check about. This time it looks like that this contains the maximum number of groups here, and it will be the more stable. But believe me, the actuality is something different from the reality is something different. CH2 and then CH3. So guys, it's like this, that how many alpha H can you see here? 0. Where is the alpha carbon? Yes, this carbon is alpha, directly connected to benzene, and we can also see that doubly bonded carbon next to it. So if it is 0, how many alpha H can you see? 1, and alpha H over here is 2. So this will show no alpha H, actually no hyperconjugation, but this will show plus H, and this will show more plus H. See, if we talk about the inductive, so inductive can be explained but still not needed. Electron donating tendency will be highest for the third one. So now check it, the correct answer, check out the correct answer. A should be the correct. And that was literally a good question. That was a very good question. So now is the another free radical, the only remaining one. But guys, this is pretty much similar to the carbocation. So you can check out that whenever ultraviolet light or sunlight is given to a bond which is having similar electronegativity gap between them, then it dissociates into giving you the free radical. Inductive effect, if we talk about, again it is an electron deficient species because it contains only 7 electrons in its valence shell. It wants more number of electron, it wants to complete its octet. So electron donating, so its stability of free radical directly proportional to electron releasing group or electron donating group, inversely proportional to the presence of electron withdrawing group. We have hyperconjugation effect. So hyperconjugation is what? Hyperconjugation, stability is directly proportional to positive H effect is directly proportional to the number of alpha hydrogen. Then resonance effect, we already have seen resonance. So it is directly proportional to stability, directly proportional to the positive M effect, and inversely proportional to minus M effect. Then we have general order of stability, and general order says that 3 degree, 2 degree, 1 degree and 0 degree or methyl, exactly like the carbocation. So we have finished with all of these three, and now starts the another important part or another important topic, that is called as rearrangement of carbocation. So we'll know about the rearrangement. Okay everyone, let me give you one question and then I'll explain ki how does it happen. Question is very simple. We have CH3, we have CH2B, we have CH2Br, one molecule of carbon, and we are reacting it with aqueous NaOH, and in the presence of aqueous NaOH we expected two products here. We actually got two products. One of them is CH3 CH2 CH2OH. Okay, it's a displacement reaction, right? So minus will be NaBr, NaBr will be subtracted, let's say, and the final product will become this. But believe me guys, this product is actually minor. This product is actually minor, and the major product you will get is CH3 CHOH CH3. Then how come this is the major product? This is the major product because this is not even a substrate given to our question. See, this was not even given. Then how come is that correct answer? That is all because of the rearrangement. So we will try to understand the mechanism of this reaction. So the mechanism says that CH3CH2 CH2Br in aqueous medium, water as a medium, it dissociates this molecule CH3 CH2 CH2 positive plus Br negative. In the first step, this is formed. This is a carbocation. Now this carbocation undergoes rearrangement. How? I'll show you. It undergo rearrangement 1,2 hydride shift. It goes rearrangement as 1,2 hydride shift. One of the hydrogen from this basically attacks to this. So what will happen? CH3 CH and this will become CH3. H minus, after accepting H minus, CH2 positive becomes CH3. And the one from where H was actually removed, it will become CH positive. Now in next step, this NaOH will come and this will attack over here. So this gives you the final compound CH3 CHOH CH3. This is the mechanism. Now you please have a focus here everyone, that what did we do, how did we understand this part of rearrangement of carbocation. This is the rearrangement of carbocation. So now we'll see how many number of shifts actually happens. So types of shifts. Shifts means there could be 1,2. Okay, mainly shift happens 1,2 only. 1,2 hydride shift. Then we have 1,2 phenyl oblique aryl shift, and then third we have 1,2 alkyl shift, methyl, ethyl, propyl, butyl, like that. So How are we deciding which should go first? This is decided by the migratory aptitude. Migratory aptitude of groups. Like which one should go for migration or shifts first? So what do you think? So guys, the rate of shifting is actually telling us it's very easy that rate of shifting, this 1-2 shifting which we are doing, is directly proportional to electron density. We all know the most electron density is carried by the smallest anion, which is H minus. So the order becomes H minus shifts happens the fastest, then phenyl shift, then 3 degree alkyl, then 2 degree alkyl, 1 degree alkyl, and then simply methyl shift. Is this part clear to everyone? Clear? So for example, if we are given with benzene and benzene attached somewhere, benzene is connected with electron withdrawing group. Benzene is simple benzene without any group, and then we have benzene with a electron releasing group. This is the order of migratory. Getting me? Now I'll show you one more important part from here. I will give you some of the questions and you will find out what will be the possibly shift in that. Okay, let me give you one question, very simple question. Do the correct shift, do the correct shifting in rearrangement. Carbocation. I will give you some of the examples, and there are so many examples with proper drawing, proper geometry. So I am just carrying this assignment with me, and I will give you some questions to solve. Let us suppose this is a question, and what kind of shift it will do, you also may write that. Start. Everyone, please do. Please do these examples. It will literally clarify everything. Okay, thank you. Thank you, everyone. If you are enjoying this lecture, please like the session. So let us try writing their correct shift. So guys, this is hydrogen there. Definitely, if hydrogen is there, there is no substitute of hydrogen. Hydrogen shift is the fastest. So 1, 2. H minus shift occurs. 1, 2 H minus shift will occur. Hydrogen will come here. So guys, what will happen? This is hydrogen. This comes with the electron density and connects to this carbon. And right after departure of this, electron density will go. This hydrogen is coming with hydride, so H minus. So this will create a positive charge here. So see. So this is 1 degree, this is 2 degrees, this is more stable. Shift has to be done into that direction only where you can get the more stable carbocation. Let me just rewrite this phase. Shift will only done, note, shift will only be done to acquire or to form more stable carbocation. If you are not getting more stable carbocation, then you cannot do the shift. Not required. Similarly, here also, one hydrogen is here. So again, when 1, 2 H minus shift, hydrogen will be shifted and then it will become positive. Like that. Then again here, this is also 2 bonds, 3 bonds. So one hydrogen will be definitely be here. So like this. So again 1, 2 H minus shift gives you what? Here it will be the positive charge now. Then what do we see, guys? Like whether it is required or not. Like see, if one hydrogen might be there, 2 hydrogens are here. One hydrogen with its electron density goes and attack here. So what does it form? Positive charge. My question is, this was still 2 degree. This is a 2 degree carbocation. This is also a 2 degree carbocation. Is it required to do the shift or not? Should we go for the shift or not? My question is to every one of you, those who are enjoying this lecture. So the correct answer is that alpha hydrogen in initially, how many alpha hydrogens can you see? Number of alpha hydrogens are 2 plus 2, 4. But the number of alpha hydrogens here are 3 plus 2, 5. So yes, it will undergo this shift. Yes, it will definitely go for the shift. Next, now I'll directly do, will not write down hydrogen or alkyl. See, there is no hydrogen, only 1, 2. We call it Me shift, methyl shift. Me minus also you can write, Me minus group will come. And one group will completely shifted here. So what does it form? Like that. And positive charge over here. This is 1 degree now, that it has become 2 degree. We know that resonance can occur if it is benzylic carbocation. If the positive charge would have been here, resonance would have occurred. So here, from this, hydride shift will take place because hydride shift is more common than even phenyl shift. So this hydride shift will take place. 1, 2 H minus shift. So what does it give to you? A benzene. Next carbon 2, it will acquire a positive charge. Now it is resonance stabilized. So always remember that shift will happen into that way only where there is a so-called or so-formed product will be more stable. So now again, this is the 2 degree carbocation. This is a 2 degree carbocation. So what should I do? 1, 2 hydride shift. This will one hydrogen might be here, go there. So it will form this is your 3 degree carbocation. So shifting doesn't randomly happen. Shifting happens only there where the so formed carbocation is more stable. Okay, just go through it, give me a sec, and then we'll continue from here. Wait. Yes, guys. So what we'll do now, we have other things to complete. Let me put the charger. Okay, finally. Now I lost the pen somewhere. So now we'll move forward and now we'll discuss about other type of rearrangements. So we call them rearrangements in cyclic carbocation. Next heading comes rearrangements in cyclic carbocation. Rearrangements in cyclic carbocations. So guys, in cyclic carbocation we generally do two type of basically ring opening and ring contraction and ring expansion. So one of them is called as 1,2 ring expansion, and then we have another 1,2 ring contraction. I will also explain like where we are gonna to use these things. So guys, usually what happens, if 4-membered ring is there, then this will go in expansion to form a C5. C5 is more stable, and if C5 is having the same, then it will undergo for C6. Ring expansion is happening here. Okay. So when does it happen? It usually happens when positive charge is on the carbon next to the ring, then expansion occurs. Okay. One of the example can be, very good example could be, let us suppose this is a particular example. So guys, this can undergo 1,2 ring expansion and will be undergo formation of this. Now how that I will explain you. Similarly, in the case of if we talk about ring contraction, so guys, contraction occurs where like C7 can be converted to C6, or a C4 ring can be converted to C3, forming what? CPM. This will form what? CPM. So this is how they contract. So when does it happen? So when the positive charge is on the ring itself, whenever the carbon atom having this positive charge is a member of the ring only, then only we undergo this kind of contraction. Now let me take you to one of the example, 4 to 3. So let us suppose this is an example where 4, you can check this charge was on the next carbon next to this ring. Here on the ring itself the positive charge is there. This will undergo 1,2 ring contraction and giving you a compound like this, CPM. This is CPM. So this is, I'll explain you now. This is called as 1,2 ring expansion, 1,2 ring contraction. So let us first discuss the ring expansion. So 1,2 ring expansion. Now first we will go for the 1,2 ring expansion. How does ring expand? The mechanism is very simple. Let us suppose this is one carbon atom, this is one compound that we'll understand. I told you that positive charge should be on the next carbon which is next to the ring, not a member of the ring. So guys, always name, number these so that you can be very much informative by that time. So this is how it happens. One of the bond breaks and electron density from here connects to somewhere else like this. So this will attack here. So in order to remove the confusion, what you can do, you can draw a transition state. So basically a transition state will come, which is no real transition state. This is how it look like. One bond will be broken. So this broken bond will somehow look like this. And one bond will be formed. This will be looking like this. And this bond will not break. This is as it is. So this is how it look like, right? And with a positive charge. With overall a positive charge. And this is 1, this is 2. So now you can see there will be a 5-membered ring formed. So you usually simply make the 5-membered ring and just simply assign 1 and 2 charge somewhere. So let me just call it 1, this is call it 2. So 1 will be having a positive charge here because from 1 we are breaking the bond, the valency will be decreased from here. There was already 4 bonds and now we are removing 1 bond. So definitely there will be a deficiency of the valency and this will acquire a positive charge. Now tell me, is it understood or not? Is it understood or not? And then what are we doing? That is what we should take care of. That numbering should be in such a way that positive charge should give in number 2 so that it will be very much convenient writing down the expression. This is called as 1,2 ring expansion. Let us take one example. Let us take one simple example. Let me pick my notes if some good example is there. Yeah, it's no, it's not a good example. There is a good example. Very simple. See, so now you mark this as 1, mark this as 2. If you want, you can make the that state also. Which bond you want to break? Either of the bond you can break, this one or this one. Let's say this one I am breaking because both of them will give the same result, so don't worry. So this will be broken down. This is as it is. This will be formed. This 2 is as it is. This is 1, this is 2 with a positive charge. Positive charge will go on that from where you are breaking the bond. This is on 1. From 2 to 1 it comes. Right, so charge comes from positive charge comes from 2 to 1. Positive charge comes from 2 to 1. Everywhere it will the same will happen. So final product will be assign number 1 and 2 to anyone. Let's say this is 1, this is 2. 1 will be having a positive charge. Okay, now I'll take you to another ring expansion. Now we'll understand ring contraction. 1, 2 ring contraction, and then we'll solve some questions and that's it. That will be the enough for carbocation and its remaining part. 1, 2 ring expansion is done. Then we have ring contraction. So take this example, everyone. Ring contraction. As I told you, the ring itself will be having a positive charge. So from wherever you want to break the bond, you should give the number as 1 and a 2. And again the same thing will happen. charge goes from 2 to 1. So you got to give the number in such a way that positive charge bearing species will be having a 2 charge. This could be 1, this could be 1. Either of them can be picked. Now you try to do this thing, that this is the electron density and this will be attacking over here. This bond will break, this bond will be formed. So now let's check it out. It is undergoing 1,2 ring contraction. 1,2 ring contraction. What does it make? This is how it look like. This bond will be broken. This bond will be as it is. This bond will be formed. No doubt the positive charge still, or you can simply just show the positive charge wherever it is. But now you break this bond. Okay, now 1, this is 2. So finally what will be formed? 4-membered ring. 4-membered ring, and this part is actually 2. This is, let's say, 1. This is, let's say, 2. So if this bond is formed, if this bond is broken over here, and this is how it is formed, the positive charge will come here. So this is how it look like. One. This is your final product. Now let me check if some better example is there, or okay, in the similar way we can take another example such as cyclobutyl carbocation. Cyclobutyl carbocation will undergo 1,2 ring contraction. What it will do? Same thing. This electron pair will attack, and this is 1, this is 2. So a triangle will be formed. This bond will be formed. This bond will be broken, and this is as it is. This is 2 with a positive charge. This is 1. So what is the final product? Like this. This is 1, this is 2, or we can simply make it CPM, cyclomethyl propyl carbocation with dancing resonance. This is your dancing resonance. Chale, now I'll give you some of the examples on the rearrangement only, and then we'll see how much did we get learned from here. So let us try some questions which are given here, and then we'll move to the next part. The carbocation CH3, CH3, CH2 positive, CH3 stabilizes itself by. So we do not have any hydrogen. So no doubt the only shift that can take place is the methyl shift. And what will be the product? 1,2 Me shift. Me means methyl shift. Methyl with a negative charge. So this will be the final product, CH3, CCH3, and this has been removed. So this is a positive charge. Here it will be CH2 and then CH3. So CH3 minus shift will take place, C. Next we have darkly acidic nature. Okay, I'll give you some questions until then. Let me just give 2 or 3 rearrangement based question so that you can become more confident in these questions. Examples. pH, pH, and a positive charge here. So you need to find out the final product and take one more example. Do it. Okay, now you people try these two questions, very important questions. So this will give us the idea about the rearrangement and their implementations and their uses. So guys, again I told you, just pick whatever the uh, carbon is bearing this charge, positive charge S2. The bond that you want to break, if this is a positive charge, we can break it from either of the side. This side also we can break the bond from this side like this, and take this as 1. So this is how the bond will be formed. So see, I'm making in this structure only. This pH was already there, this is formed, and this has broken, and this is pH like this. See how easily can I do it. This is your 1, this is your 2. Another way of representation, same here. One where is pH, another side is here, pH. This is. Try this question. Now what I see, should I undergo contraction or expansion? What do you think? Now 6-membered ring is already stable. This ring is already stable. Six-membered ring is already stable, even more stable. So this can undergo. Okay, just put this thing as 2, this thing as 1, and I told you electron density. Pick the electron density and get it tagged. What do we call it? 1, 2. Okay, what was it? 1, 2. Ring contraction. And what is it happening? 1, 2. Ring expansion. So what happens in ring expansion? This will attack down over here. Simply first keep this thing as it is. Now next you attach it there, here, and like this, and there is a positive charge from where we have broken the bond. This is the positive charge. This is your 1 and this is your 2. So now you can again just see, this is the beauty, that I'm just picking the structures as it is and just moving the bond, from breaking this bond, detaching from here and just attaching here. Now see, this is how it look like. Now what you can do is, now you all know this is nothing but simple this is your compound. Too much is left here. So anyways, now we have reached to the acidic and basic strengths. So let us just start acidic and basic strength from here. That is it up to this. Then we have acidic nature of organic compound. Okay, so what is an acid? First of all, let us discuss the part what is an acid. So guys, an acid could be HA, and let's say HA reacts with water or in aqueous medium. This is an aqueous, this could be liquid, and let's say it equilibrates. Equilibrium constant is said to be Ka, and it forms H3O plus or H plus aqueous plus A minus. So basically its Ka will be defined as H plus A minus divided by Ha. So when can we say that acid will be more acidic or it's a stronger acid? So basically acidic strength is directly proportional to the concentration of H plus, and it is directly proportional to the what? Concentration of H plus is directly proportional to what? Ka, and it is also directly proportional to the what? Concentration of A minus. Or we can simply say that higher is the stability of A minus, higher is the acidic strength. Very simply, higher is the amount of A minus formed, higher will be the H plus formed, higher will be the value of Ka, and higher will be the acidic strength. So what we can simply conclude is, sir, pKa is equals to negative logarithm of Ka. So higher Ka means, simply we can write like acidic strength increases if Ka increases and pKa decreases. That's a simple relation. First of all, pK increases, then Ka decreases, and then acidic strength decreases. If you want to increase the acidic strength, Ka increases and pK decreases. First thing. So we can simply say that acidic strength of an acid is directly proportional to the stability of its conjugate base. Its conjugate base. So basically anion should be stable. So stability of anion also depends upon so many factors. Stability of conjugate base oblique anion depends upon following factors. What are those factors upon which this depends? Number one, electronegativity of atom bearing the negative charge. So this is, guys, remember, applied along the period. When the elements belong to the same period, then this concept is applied. Take this example. Carbon, methane, ammonia, water, HF. So if we have to discuss their acidic strength, do one thing. First you remove H plus out of them. Acid will remove the H positive and will form a conjugate anion. So what will be the conjugate anion? F minus, OH minus, NH2 minus, CH3 minus, CH3 minus. Now what should be the stability? We all know the electronegativity. The electronegativity is, we all know that carbon has less electronegativity than nitrogen, oxygen and fluorine. To follow the same order. So this will become the order of stability. This will become the order of stability. If this is the order of stability, this will become the order of Ka. Ka bole to acidic strength. This will become the order of Ka. Now you people please write this thing down, make proper notes out of it. Then I'll take you to another beautiful example. Okay, then we have next number 2. So the initial was the electronegativity, then the size of atom, size of ion, simply size of the ion, and usually works in a group, member of a group. Let's say I talk about HF, HCl, HBr, HI. So after removal of H positive, it will give you F minus. After removing H positive, it will give you Cl minus. This will generate Br minus, and this will generate I minus. Now you compare all these. So what do we see? That this is the order of size. Anyways, electronegativity, if this is no. So basically, always remember, I forgot to mention this part, that stability of an ion is directly proportional to electronegativity. So here what do we conclude? That stability of an ion is directly proportional to the size of an ion. Bigger is the anion, higher is its stability. So this is the order of size and stability. So since I minus is more stable than F minus, it will become the most basic. So simply the order will become this. This is the order of acidic strength Ka. Next comes your 3. Presence of a group. What is the meaning of group here? So group means we can simply say that stability of conjugate base oblique anion is directly proportional to the presence of electron withdrawing group. If there is an electron withdrawing group, it will make it more stable, and inversely proportional to the presence of electron releasing or donating group. Very simple. take this example. There is a CH2F COOH, then we have CH3COH, and there we have CH. Now tell me which of them is the most stable. So guys, you can easily see that this part is actually minus I. There is nothing over here. This part is a plus I group, and plus I group does what? Okay, we can do one more thing. Let me not complicate this part. We should take this. So we know that what does this part do? Plus I. So plus I will basically after removing the H plus, it will make it more unstable. So this is the correct order of Ka. Wherever I write Ka, that means it is the order of acidic strength. This is the order of acidic strength. So now I'll do a bit comparison between very popular important chemical compound that we discussed yesterday with some good functional groups. So let me just first take you to number one. Number one is carboxylic acid versus sulfonic acid. Carboxylic acid versus sulfonic acid. So guys, we all know that both of them are good acids. Priority wise, carboxylic acid is dominant, but acidic strength wise, let's see who wins. So we'll go for some short comparison between all the acids. So let us say carboxylic acid is R, C double bond O, OH. After losing a H positive, it gives you R, C double bond O minus, and R, C, O minus double bond O. So basically what you get is two equally contributing resonating structures. Go with sulfonic, R, S, O. RSO3H. So what will happen RSO3H after losing a 1H positive? It gives you R, S double bond O, O minus, R, S, O minus, double bond O, R, S, O minus, double bond O. Now you check it out, all three. So how many number of three equally contributing resonating structures. So now tell me which is more stable. So these are more stable. So who has won this fight? Conclusion. Conclusion is that RSO3H is more powerful acid than RC double bond OH. Remember this point, guys. This will be very much useful. I'll tell you all the possibilities. Give me a sec. Yeah. Next, let us carry out this between number 2 RCOH versus PHCOH. What is PHCOH? This is called as normally alkyl carboxylic acid versus बेंजाइलिक बोलते थे ना, बेंजोइक एसिड, बेंजाइलिक क्या, बेंजोइक. Let's see who wins. So guys, after removing H positive, it forms RC double bond O minus, and this R is providing plus I effect. After losing H positive, this will form O minus, and this provides minus I effect because sp2 hybridized carbon. Benzene has a minus I effect. So which one is more stable? This one is more stable. If this is more stable, then what will be the conclusion? The conclusion is pretty obvious, that RCOOH is lesser acidic than benzoic acid, PHCOH, and this works for everyone. In fact, even for also PHSO3H is more acidic than RSO3H. Even guys, you will also notice that if we go for formic acid HCOH, CH3COH, C2H5COH, C3H7COH, this is the order of Ka, that it decreases with the increase in the alkyl size, because I effect will be increased. But it's a very interesting part, but practically it has been observed that HCOOH, which is called as formic acid, is even more acidic than benzoic acid, and then comes your rest of the members RCOH. This is the order of Ka. Right, but if you apply any electron withdrawing group, HCOOH is there, and let's say CH2Cl COH is there, then it will become more acidic. So learn these things accordingly. I hope this part is very much clear to all of us. Now let me give you one small question here, and I want you people to write the correct order of acidic strength. Write the correct order of acidic strength. So out of these, we have to tell what is the correct acidic strength order. Now you people try it by your own. So we all know that Ka is directly proportional to the electron withdrawing group, and that is minus I over here, right? So if you check it out, this is closer, just next to it, so minus I. This is very close, so this is very good, minus I. This is somehow far, so smaller, minus I. This will be very smaller, minus I. So now you compare this and you will get the answer that second is most acidic, followed by first, followed by third, and then followed by fourth. This is the answer. Next comparison. Now we'll have the next comparison between, let me check who's in the list. Okay, so we'll compare now. Number 3 will compare ROH versus RCOOH. So I think alcohol versus carboxylic acid. Simply carboxylic acid must win. How? Because guys, what will happen if you remove a hydrogen atom from alcohol, it will become RO minus, and this R group is giving it a positive I effect, so this is becoming unstable. And now if we talk about carboxylic acid, after removal of carboxylic acid, minus H plus, it will give you RC double bond O minus, which is resonance stabilized. Check it out. Reso stable. So no doubt conclusion is alcohols are not that acidic. Carboxylic acids are more acidic than alcohols. Now fourth comparison is very beautiful and very interesting. Fourth comparison says that we have to compare, I will compare, this is ROH. Now we'll compare phenol versus carboxylic acid, normal carboxylic acid. This is very interesting. So guys, what will happen? This is phenol. This compound is called as phenol with OH group. When it loses H positive ion, it becomes O negative phenoxide ion. this has become phenoxide ion. So what is happening in phenoxide ion? Phenoxide ion has its resonating structures like this. See, so how many resonating structures can you see? 1, 2, 3, 4, 5. Basically, what we are getting is 5 resonating structures. So what we can see, dominant? No, it seems dominant. Let's see who wins. I don't know. But comparing to carboxylic acid, simple RC double bond OH, yeah, what's wrong? After removing H positive, it gives you RC double bond O minus, which is RC. Another structure would be this. But these two are two equally contributing, two equally contributing resonating structures. Now you tell me which is more stable. So guys, believe me, RCOO minus is more stable even than PHO minus. Why is it so? Because RCO minus ion has two equally contributing resonating structures. Also, the negative charge of this acetate ion lies on more electronegative atom, which is oxygen, thus more stable than phenoxide ion. Because phenoxide ion didn't give you equally contributing, and it is giving you equally contributing. So that is a very amazing reason behind it that gives you a conclusion very simply. Let us jump to the conclusion. What do you think? What should be the conclusion? That RCOH is more acidic than PHOH. So guys, let us now go to another factor, fourth or fifth, I don't know, let's say fourth. So let this fight be against alkane, alkene and alkyne. Alkane, alkene and alkyne. So what is alkane? Let's say CH3 single bond CH3. Alkene, let's say CH2 double bond CH2, and this is CH triple bond CH. So after losing one hydrogen, it will form CH3 CH2 minus, it will form CH2 CH minus, and it will form CH3, sorry, CH3 no, CH triple bond C minus. So now electronegativity of carbon sp3 sp2 sp sp. So guys, this is what we can observe here. This is your sp, this is sp2, and this one is sp3. So electronegativity follows this rule. So this is the order of stability and this will become the order of acidic strength. See how easy. But one thing that we observe is this: note nitrogen sp3 is more electronegative than carbon sp3. Nitrogen sp2 is more electronegative than carbon sp2. Nitrogen sp is even more electronegative than carbon sp. But carbon sp is more electronegative than nitrogen sp3. Nitrogen sp3 in the terms of electronegativity. What we are talking about, the electronegativity. So what we can simply conclude that CH triple bond CH is even more acidic than NH3. Okay, remember this part. Now right after that I'll give you a complete example. This is where we end with the acidic strength. I'm giving you a like overall view of acidic strength, overall question. Sir, voice is very clear than yesterday. Okay, thank you. So like the session, dude. Not this question. First of all, I'll give a very huge question that will almost cover all the compounds. Now one thing also we should cover, fifth part is ROH versus H2O. ROH versus H2O. What do you think? See, ROH if loses H positive, it will give you RO minus, and this after losing H positive will give you OH minus. This is more stable because this R is giving you positive I effect, making it less stable. So guys, make a note that alcohols are taking 1,6. Okay, alcohols are, the water is more acidic than alcohols. Except CH3OH, methanol. So basically this is something which is experimentally driven. So remember, always remember that H2O, CH3OH is more acidic than water, and then rest of the alcohols will come, even ethanol. This is the order of, okay. Now I think we all are ready for the final challenge of the day. Final challenge of the day, final question of the day. We have to find out the correct order, the correct sequence, right? Second. Then we have then we have so guys, out of these we have to give the final order of acidic strength, comparing all the compound. Now I'm comparing all of the possible compound. Right. Question is very simple. Arranged in decreasing order. Arrange in decreasing order of Ka. We have to arrange the given compounds in the decreasing order of Ka. I'm giving you some time, you can try it by your own. Now let's see who can do it, then I'll explain. Okay, so thank you AAVV for appreciating my voice. It is louder than yesterday, and thanks Deepika. क्या बात है. So anyways guys, where were we? Yeah, I was about to disclose you the correct order out of this all. So what I personally find answer. Okay, I'll get to one side once, then I'll explain. So we all know that sulfonic acid is always more than benzoic, and also benzene sulfonic will be the strongest one, followed by normal sulfonic acid, followed by, we know that benzoic acid is more, but this is even stronger acid than formic acid is stronger than benzoic. Then we have benzoic. Where is benzoic? First. Then we have phenol, sure, because rest of the have been already covered. Then we have sixth, which is phenol. Then we have alcohol, and we all know that methanol is even stronger than water. So then comes the methanol. Where is methanol? Eighth. Then comes water. Then after water, rest of the alcohols, such as like 3 degree will be even more worst. It will be worse alcohol, because the O minus charge will be highly unstable by 3 large size groups of giving inductive effect. So now I'll simply take any of the secondary alcohol. Then 7th will come. Then after 7th it comes 9th. Then after 9th it comes, okay, so we know that alkyne is even better acid than ammonia. So this may come 14th. Then ammonia. Then alkene. Alkene is better than alkane. And then the last is alkane. This is the order of acidic strength Ka. What a question it was. The greatest question. The greatest of all time. So now guys, after this we'll study about phenol and substituted products. Okay, so very simple. Now we'll study the acidic strength of phenol. So very simple, we all know about phenol. What does phenol do? Phenol in water loses H positive and gives you phenoxide ion and one H positive. We also know that Ka is directly proportional to the stability of phenoxide ion. So one more thing there will work. So we can say that Ka is directly proportional to the presence of electron withdrawing group and inversely proportional to the presence of electron releasing group. This is the fact about phenol. Also guys, if there is a mesomeric effect operates, so that we have to take into account. If any electron withdrawing group is at ortho and para -m or minus H. Reduces electron density, stabilizes phenoxide ion. So if let's say this is a compound and somewhere we have connected NO2, this is a normal phenol and this is a phenol with containing CH3. Now what is the working of these three compounds? This compound has minus M effect more than minus I. This compound has nothing. This compound has positive hyperconjugation more than plus I. So this is electron releasing group. This is electron withdrawing group. So the correct order should be this. This is the order of acidic strength Ka. So I'll give you a few questions on this and then we'll move forward to another point. क्या हुआ ये? See, solution. We all know what does CH3 do. It is nothing doing here. CH3 gives you plus H more than plus I. But here at meta position, only this plus H, which is a kind of conjugation. Every conjugation work only at ortho position, ortho para position. है ना? How that I'll also tell you. But now, as of now, just take this idea that any group which is present at the ortho. Because guys, we know that electron donating group always, like that plus M group always gives you the electron density and that appears on the ortho and para positions. So due to that, it will stabilize it or it unstabilizes it. So this is giving conjugation and it is unstabilizing this part. Here it is only doing the positive I effect. Here we can see it is also doing positive H more than positive I. Ortho and para going the resonance, at meta it only inductive. So correct order of Ka should be, so best is without anything, then inductively, then more plus I will be over here. So then fourth and then comes your second. 1342. 1342. Let me check. Right. Then talking about this, it has nothing. Cl minus does more minus I than plus M. There is no chance of plus M here because it has meta position only minus I, even smaller because distance has increased. This is even more smaller minus I. So what do you think? What should be the correct answer? The order of Ka. So we must know how to identify the nature of a group, and there are some set of groups that will be repeatedly used. So please take the idea. What is wrong with everything here? K will become closest and a very good minus I. Then we have a bit far, and we have the farthest. And then we have first, like this. So this is the order of acidic strength of phenol. Let's say if I attach, this is phenol, and if I attach nitro, here nothing, ortho nitro, meta nitro, para nitro. So solution. So this will be nothing. This will give you minus M more than positive, sorry, minus M more than minus I. This has only minus I. This has very, but it's M more than minus I. So the correct order should be, but here also we have a intramolecular hydrogen bonding, and because of this hydrogen bonding, this H plus doesn't leave easily because hydrogen bonding is connecting this hydrogen to the nitro group. So the very first, it should come with fourth, then comes the third, then first, and then becomes the second. This is the order of K. Third, first, second. No, not like that. Bit changes here, not that much, doesn't affect, not that much. It's fourth, second, third, and then first. So this ortho substituted has come right after the para one. So that is it, everyone. This is a very huge topic. There is a very vast topic. There are so many things that we cover under this topic. So till now we have discussed about the acidic strength of phenol, and now we will discuss the acidic strength of benzoic acid. And there we will be studying SIR effect, SIR effect, steric inhibition in resonance. Anyways, we'll come to it. We'll take a break for a short while and then we'll connect back. Then we'll finish the remaining part of this chapter, which is acidic strength of carboxylic acid and basic strength of some normal nitrogenous bases. So acidic strength of carboxylic acid. So this is your benzoic acid. We call it Ka, and it dissociates into CO minus benzoate ion plus H plus. So Ka is directly proportional to the stability of benzoate ion, right? So from here we'll continue very soon, guys. It's a 15-minute break we'll take, and then we'll continue the class till 10 o'clock. So you better have your dinner, and then we'll contact back. एक सेकेंड। Yeah, hi guys, I'm back. So now let's start it. That was a very good 15-minute break, very healthy break we had. So it's a dinner time by the way, but couldn't manage dinner here, so I just took one coffee and came back. Some coffee and some cookies I had. And now we'll just wind up the session by finishing this very important part of acidic strength of carboxylic acid. So what is carboxylic acid and how does this operate with SIR effect? What is it? So guys, if you see, no, what is it? Let us talk about the carboxylic acid and benzoic acid if it is connected to COOH group. And if benzoic acid contains any group which is electron releasing group, now it may be present at ortho, meta or para, it doesn't matter. It will definitely be a weaker acid than normal benzoic acid as we just discussed till now, because presence of electron withdrawing group makes this acid even stronger and stabilizes its conjugate anion. This is the order of Ka. But if we apply an electron withdrawing group, over meta and para, not ortho, then this will become a stronger acid than benzoic acid. This is the order of Ka. But interestingly, very interestingly, if benzoic acid is connected with any group G at ortho position, and let it be an electron withdrawing or electron releasing group, whatever be the nature of this group, this will always be a weaker acid than COOH, normal benzoic acid Ka. And this is called as, oh wait, this will be a good acid actually, not a bad acid. It will be a stronger acid. And this is called as the ortho effect. And it is explained by SIR, steric inhibition in resonance. So this is the most beautiful part which we are gonna to cover for all the benzoic acid, okay? Benzoic acid. So why is it happening? Let us check it out. Let us suppose this is the benzene ring and this is your C double bond of OH. So what I'm doing is, if you remove H positive, it will become benzoate ion. So guys, this benzoate ion want to get stable, but meanwhile this creates a cross resonance. Because of this cross resonance by benzene ring, it destabilizes the anion. So what we should do? We are simply removing this. We are simply removing this conjugation of benzene ring by applying a group G at ortho position. Now what happens after removal of H positive? And we all know that this is benzoate ion and this is group G. Because of the influence of these two bulky group, due to hindrance, due to this hindrance, this COO minus group, this CO minus group goes out of the plane. Out of the plane of benzene ring, and due to which benzene cannot do the resonance. Now, not possible. So if it is not possible, that means it will be more stable. So anything which is connected to what? If anything is connected to the ortho position of benzoic acid, it will always be more acidic than the one with like normal benzoic acid. Where is this? देखो देखो So now we'll try some questions, and that's the end of the acidic strength. So let us try some questions. This is the benzoic acid. First, let us suppose I am applying CH3 group first. But you might be wondering, why wasn't it operating in the case of phenol, right? So this G can be any group, can be any group not lighter groups such as OH, NH2, cyanide, etc. These groups are not affected by the hindrance or bulkiness of the group. These are very light groups, and these light groups do not interfere in steric inhibition in resonance. So now again we are coming over this example, and that is why we were not considering this the same point in when we were doing the same for phenol. So now coming back to our topic, this is second, this one is third, and this one is the fourth. So we have to find out their order of acidic, or there is an order of acidic strength. So guys, here nothing is working. Here positive H more than positive I. Here positive I only, because no hyperconjugation works, no conjugation works as the meta position. Then it has plus H, then plus I. Here beyond this, SIR, SIR effect works, steric inhibition in resonance. So basically this is steric inhibition in resonance. SIR. So SIR effect dominates, second will become highest, followed by first, then comes third, and the worst one will be the fourth, because it is creating plus H effect and making benzoic acid a base weak acid, making it a even weaker acid. So similar kind of examples can be taken, everyone. Depending upon the nature of group, we have to learn. So let us take this example. This is phenol, this is our benzoic acid. This is first. The another benzoic acid with, let us say, suppose OCH3 is the group right now I'm taking. Second, third, and fourth. So first, second, third, and fourth. Apply this question. Solution. What kind of group is this OCH3? Here is nothing operating. OCH3 gives positive M more than minus I, but more than that SIR works. Here only minus I works. Here plus M works more than minus I. So the correct order of Ka should be what? The best test will be second because of SIR effect, followed by third, because third is giving you minus I. Then we have first, then worst one will be the fourth. This is the order of K. So these are some sort of very good examples I'm giving you. Let's come to the another example. This time I will apply Cl minus group, Cl group, COH, simply COH with Cl. See the solution. No effect is working here. This is minus I is dominant over plus M for halogens. Remember this part. Only fluorine has a similar inductive and nearly comparable inductive and mesomeric effect. Rest in other cases, halogens are bigger sized. This belongs to 3p. This is 2p. 3p 2p intermixing is not that well, and that is why chlorine and beyond that they will be having minus I effect over positive M effect. Then we are here, but more dominant effect will be SIR. Then here only minus I operates. Here minus I operates beyond plus M, but smaller minus I because this is distant apart. So what will be the order of Ka? The acidic strength will become what? Second will be the best. Why? Because of SIR effect. Then minus I effect is working in third, then in fourth, but a bit lesser, and then comes the first. This is the order of Ka. So guys, everywhere you will be getting different answers. Everywhere you will be getting different answers. You cannot rote learn anything. You cannot just wrote it down. You cannot just learn it without concept. You have to apply the concept. You should get the final answer accordingly. Last example on acidic strength, and then we'll complete acidic strength and we'll finish it. The another example could be benzoic acid. Benzoic acid at with NO2 group. NO2. NO2. First, second, third, fourth. Solution. So guys, what do you see? What is operating here? Nothing. This is minus M more than minus I, but beyond that SIR effect dominates everything. Minus I will work here, either minus I more than minus M more than minus I, okay. But mesomeric is distance independent effect, inductive is distance dependent effect. So what will be the order of Ka? So the Ka order will be, best will be the second. SIR, sir wins, sir always wins. Then fourth, because fourth has an mesomeric effect negative. Then third, and then comes the first. Like that. Which of the following is the weakest acid? Weakest acid one will be the one in which this will go and destroy the stability of an anion. So B is the worst one, weakest. Arrange the following compound in decreasing order of acidity. Acidity means like acidic strength only, it has been asking. So how are we gonna to find this part? How should we approach? By the way, what I'll do, see, we must know the nature of each and every group. OCH3 does positive M over minus I. NO2 does minus M over minus I. this does positive H over positive I, and this does minus I more than plus M. Now you decide it which one of them is more dominant. So I think 3 is the best out of all of them, nitro group. And then I will go for first, then I will go for second, and then finally I'll go for fourth, because fourth one is giving resonance and it is like weakening the acid by providing more electron density to a negatively charged anion. This is the correct answer, Ka. Check it out. 3124, 3124. I think C is the correct answer. Wow, yeah, I'm the best. Anyways, these are some set of questions you should try by your own. See, there is a base given to us, that is CH3CO minus. So base wants to attack, so this is the option or this is the option. So basically, which one is more acidic? So more acidic is this one, so it will go for this. So correct answer should be this, B. Anyways, this is your homework. Try by your own. You will get your notes directly. This is already completed. These all are homework. Try all by your own. I can't help you further. And this is something which I have already covered. This part, complete part has been covered by me, everyone. This whole complete has been done. You should try these questions by your own. So now I'll come to the basic strength of the organic compound. What is happening here? Stop, man, stop. Hold, man, hold. So now we have another important part, basic strength. Okay, basic strength. Let me just first check some of the questions from basic strength, then I'll come to the basic strength. Okay, so usually organic bases are, these are not Arrhenius bases, they are mostly Bronsted or Lewis bases, which donate lone pair to acquire H plus. For an example, RnH2. So they will do what? Attack on H plus, will form what? RnH3 plus. Getting me? Like that. So what we can say simply that for all bases, basic strength is directly equal to 1 upon stability of ion. Stability of anion. If it is an anion, okay. Bases are Bronsted or Lewis bases, or it can be guys any anion also, like X minus. So X minus can accept H plus or forming what? HX, like this. So all the bases, their basic strength is directly proportional to 1 upon stability of an ion. So let us take the same examples here. So let us say number 1, electronegativity of atom bearing the negative charge, factors affecting, basic strength. So number 1 is electronegativity of atom. So take this example. Let's say these are the bases: CH3 minus, we have NH2 minus, we have OH minus, and we have F minus. So we have to compare which of them is the stronger base. So guys, let us discuss this part first. Basic strength is inversely proportional to the electronegativity of atom, because if more electronegative atom is holding a negative charge, why would let it go? Because it is already stable. So guys, what is the order of stability? This is the order of stability, and that is why this will become the order of Kb. Am I clear here? Number two is the size of atom. So guys, bigger is the size, lesser is the charge density. So basically what we can conclude from here is also that stability of ion, and also we can say that Kb for a base is directly proportional to the charge density of anion oblique molecule. Coming to this part, size of an atom. So basic strength will be inversely proportional to the size of an ion, because higher is the size of an ion, lesser is the charge distribution or charge density, and it is already stable and it will not attack on H positive to work as a Bronsted or Lewis base. So size of atom also matters. Now let us suppose F minus, Cl minus, Br minus and I minus. These four are given to us. We know this is the order of size of ion, because down the group size increases. If size increases, then their basic strength will follow what order? Fluoride, chloride, bromide, iodide. This is the order of Kb. I hope this part is pretty much clear to all of you. How many lectures of GOC? GOC, probably 3 lectures will be there. Today is second lecture of GOC. Yesterday's lecture I covered all the basic parts, some basic phenomena, some definitions, IUPAC nomenclature and everything. Now in today's session I am completing the applications of electronic effects, and with the acidic strength, basic strength, stability of carbocation, carbon ion rearrangements. Very beautiful lecture I had today, and I'm proud of that, guys. I made the day, guys. You go through this lecture, you will find that you can solve any kind of question until you're advanced. But this is something that you have to make notes by your own, follow everything, and then only you will be more comfortable and solve some questions. But right after that we will start isomerism, which will be our last and final lecture for GOC. Right after GOC I'll start reaction mechanism. So that will be somehow related to GOC, but entirely different from GOC as well. So now I was telling you one thing, and this is the part that electronegativity, this factor, this is applied in a period, of the group, period of the modern periodic table, and this is applied in a group. Now what kind of compounds do we have to compare third one is presence of group. So guys, it is very easy that Kb is directly proportional to the presence of electron releasing group. It will increase the density. Kb will be inversely proportional to the presence of electron withdrawing group, because electron withdrawing group will decrease the electron density. So this is how it will work. Take this example. if NH2 is there as a base, we call it aniline. Three examples I'm taking. One of them is connected with NO2, another one is connected to nothing, and the last one is connected to, let's say, OCH3. So guys, do you know the nature of these groups? This one does -M more than -I. We studied today, yesterday also. It does nothing. It does positive M more than -I. So this positive M will increase the electron density. It will be donated easily. So this is the basic strength Kb. Okay, next. So now we will study basicity of amines. This is our topic, basicity of amines. So basically we'll study in two parts, one for aliphatic amines, another one for aromatic amines. So guys, aromatic amine is called as aniline, we'll discuss its basicity, and aliphatic amines could be RNH2 primary amine, R2NH secondary amine, and R3N tertiary amine. So these are the set of amines. Wait. Keshav Agarwal is asking me, sir, Singage is good or not? Singage addition is good in various ways, like what you are preparing for it matters. But I would rather suggest, instead of going for Singage addition, because Singage contains so many that content which is not even required in JEE. Singage is a good book, and sometimes even teachers also study from Singage books, because chemistry is very vast, and chemistry, that particular part that has been asked by JEE, is sometimes found in the MSc books. Master levels books are there, graduation level books are there, and we genuinely prepare notes out of that, and then we provide to students. But Singage is a good book in order to collapse so many good informations out of this book. But again, I would like to suggest you that rather than going for Singage in as a theory book, you better should buy some book to practice the questions, because theory is very well enough wherever you are studying, whether you are studying in a coaching institute or you are studying from us. The theory part that we give is highly sufficient. What you require from your end is the practice part, because practice is something which is lagging, which is missing. So you can start practicing either from the like I told you 3 books that time, in organic chemistry, VK Jaiswal is a very good book. Organic chemistry, MS Chauhan is very genuine book. Himanshu Pandey is one. And coming to this physical part, you can try Anavasthi is a very good book. We have RC Mukherjee, good book. We have P Bahadur, very good book. So these books you can follow. Rest is the things, and this everything is very much relatable. It's very much relative. People opt according to them, and you may also opt according to you. But that is what my suggestion is. I think Singage edition is some it's beyond something. It's not even required to study that much. So you can skip Singage and rather than buy what I have suggested, because these books also have level 1, level 2 kind of concepts. Level 1 concept is very much helpful in JEE Main, and even simpler questions are asked in JEE Main. Level 2 questions are good for advanced point of view. You can try advanced PYQs, you can try these questions, and you must try the theory, whatever you are following the coaching notes or us, that is good. And so that is what my suggestion is. Okay, Keshav, now look, moving forward. Where were we? We were on the basicity of amines, and we'll discuss this in two parts. Let us first discuss about the number 1 for basicity of aliphatic amines. Basicity of aliphatic amines. So we all know that primary, secondary, tertiary amines are actually containing so many alkyl groups, and number 1 we'll compare them in gas phase. In gas phase, what do you see? We want to increase the electron density, so this will become R3N with highest positive I. Then we have R2NH with somewhat lesser positive I. Then we have RNH2 with even lesser positive I, and then we have NH3 with very less positive I. So guys, this is the order. Inductive effect, positive I inductive effect, electron releasing group increases the electron density. This becomes the order of Kb, basic strength. But it is in gas phase only. But in aqueous solution, remember, this is very important part I'm telling you now. This follows an order of 2 degree, 3 degree, 1 degree, 0 degree, and it also follows 2 degree, 1 degree, 3 degree and 0 degree. This is in the case of methylamines, right? This is in the case of methylamines, and this is in the case of any alkyl amines. So this is the order of Kb. Now you people might be wondering how come is this order came like this. So now I'll explain the concept behind it. Now try, guys, check this thing out. If we compare in aqueous medium, if we compare the basic strength in aqueous medium, let us first observe all of these bases. Number 1 is RNH2, or let us say this is R3N. Then we have R2NH, and then we have RNH2, and then we have NH3. So there are two factors which are working. The number 1 is the inductive factor. The number 1 is the inductive effect, or we can say electronic effect. Electronic effect is something that says that this should be the order, because the inductive, as I told you, this is plus I, this is plus I, and this is like that. This is the correct order. But if we talk about the hydration factor, hydration effect, because we are right now in aqueous medium, so we must know that after accepting that H positive, which one of them will be higher stable, which one of them will be more stable. So now check it out, everyone. This will become what? RH with a positive charge. So now water cannot easily hydrate this because of the bulky nature of the R groups. This can be easily hydrated by water. See, and similarly this one will be most easily and most efficiently and mostly hydrated by water because of its lesser bulky nature, and like that. And then comes the NH3. So the order should follow a reversal. Order is right now opposite. See, this is the order of Kb. Then this should be the order of Kb. So considering these two factors, there is a fight between these two factors. So now if I consider these two, considering both of the above factors, if I consider both of the above factors, then what does it become? See, then the order becomes for R, for alkylamines means R group, R groups is there. The order follows what? 2, 3, 1, 0. Learn it. And for methylamines, with a methyl group substituted with it, methylamines, it becomes what? 2, 1, 3, 0. Learn these number, everyone. Learn these number. So it's very important to learn about these numbers and what kind of things I'm bringing from here. Alkylamine versus methylamine. So very easy. It's now it has become very easy, and always make this part as a note that if it is not mentioned the medium, if medium is not mentioned, whether it is gaseous medium or aqueous medium, if it is not mentioned, always consider aqueous medium. If it is not mentioned which medium we are talking about, always consider aqueous medium. Now I'll give you one question and you will see the correct answer. You need to find out the correct answer out of that. अरे यार क्या प्रॉब्लम. This is one question. Okay, first, second, third. I'll give you two questions. You need to write down the correct order of basic strength, undoubtedly. So we have ABC and we have to compare these first, second and third, and either ABC as the basic strength of the correct basic strength of these amine. So everybody please try. Okay, so what we will do, we have these two questions with us. So first one, find out the degree, guys. One is I think this is connected to 2 carbon. This is 2 degree, this is 3 degree, and this one is 1 degree. So the correct answer should be for Kb. We all know 2310 for all the alkylamines. So first will be the correct answer, first, followed by second, followed by. This is the order of Kb. Next one, try it. Only the degree has to be known. No 3 to 1. I told you, if any medium is not given, consider that in the aqueous medium only. In an aqueous medium, this order will be used. This order 2310, 2130 for methyl groups are substituted, and if alkyl groups are there, random groups are there, 2310 is the correct order. Same apply over here, ABC. So NH2 is given here. This is 1 degree, A is 1 degree. B is 3 degree and C is 2 degree. We know most basic part is C followed by B followed by A. This is the order of KB. So guys, this is how we do. I hope you all are comfortable now. You can apply the correct sequence and correct concept, correct logic. So that is the basic strength. Okay. So now after this, okay, one more example is there. I can take one more interesting example. Let me take one more interesting example here. This is nitrogen. Now you try this question. This is a beautiful question. This is first, second, third, fourth and fifth. Out of these we have to tell. So guys, see what is happening. This is a conjugation which we can see. So this will go under conjugation. So this is a resonance happening here. This is directly over here, no resonance, and but this will become what? sp2 hybrid with more electronegative. So basically this will decrease the basic strength. Here more resonance can be seen. That means it is even more stable compound is this will not easily donate its lone pair. But here it can easily do, but it is a 1 degree amine. And the final one, it is a 2 degree amine. So okay, one thing that is very sure, that 2 degree amine with nothing demotivating factor will be the answer. So answer KB first should be fifth followed by. Now resonance is actually decreasing the basic strength. Resonance is actually decreasing the basic strength. Then 1 degree should be the correct answer. 1 degree should be the correct answer. So 1 degree is actually fourth. Now resonance is worsening it. Resonance is worsening it, but this can be the correct answer. Then second, first, and then last will be third, because third has the most resonance, most stable. Anions or most stable molecule will not become good bases. Good bases will easily accept H positive from water, giving OH minus. So this is the correct order. Okay. Now final topic of the day, everyone. Thank you for being so patient. This is the last topic. I'll try to finish it ASAP. Now we have second is the basicity of aromatic amine. Basicity in aniline. So try to understand what I'm explaining. If NH2, this is your aniline, and aniline is connected with any group which is electron releasing group, then definitely sorry, not electron releasing, it is electron withdrawing. So withdrawing group will decrease the electron density. So that is why it will become weak base, then a normal aniline, isn't it? Yes, why not? Order of Kb. Similarly, if you are okay, this electron withdrawing group could be ortho, meta, or para, anywhere you can apply. Now again ortho effect will come, guys. If you have applied electron releasing group to ortho, not to ortho, meta and para, then this aniline, substituted aniline, will be a good base than the normal aniline. Very good, we know about it. But now what will happen? See, if benzene ring connected to aniline, connected to NH2 group, and ortho position there is a group, whether it is electron releasing or electron withdrawing. So in SIR effect, what did you see? In SIR effect or ortho effect of carboxylic benzoic acid, the basic strength was increased, but here you can check basic strength is decreased, and this is called as ortho effect. This ortho effect is also called as steric inhibition in protonation. This is the beautiful part about it. I would like to check what is this beauty all about. This is the beautiful part about the basicity in aniline. So how to face this? This is SIP effect. I am explaining you what happens in SIP effect. So guys, what generally happens, we all know that benzene ring is here, normal NH2 is here. After adding with H2O, equilibrates, takes H positive, NH2 will become NH3 plus, and very easily hydration occurs. So see how easily hydration occurs. Water, I'll bring water with white. CH bonding is happening. So what we are seeing is easily hydrated, or we can say stabilized. This is stabilized now. Now you apply the same thing using a group G with NH2 here. So guys, water doesn't hydrate cation easily, thus basicity decreases. Now if basicity has decreased by applying any group, this is called as the steric inhibition in protonation. Steric inhibition in protonation. This is called as steric inhibition in protonation, and this concept will help us solving so many good questions, very good questions. Now let me take you to some questions. Same thing we will apply here. Example. So let us suppose to this aniline I am applying a group, methyl group. Now you tell me what should be the correct order of basic strength: first, second, third and fourth. Solution. Try to identify the nature. Nothing. It has plus H more than plus I, but both of them will be failed. Only SIP will work, and that will make this compound worst out of every scenario. This is simple plus I, and this is plus H more than plus I. Plus H more than plus I will give you the best way. So the KB order you can write down in the increasing order also. Worst will be the second, and then right after that first, then third, and best will be the fourth, because fourth is having electron density provided by conjugation. Right, this is the correct way. Next is another example can be taken as, I'm tired now, yeah, that's it for the day. ठीक है, NH2. Guys, you can apply anything by your own, yeah. This is something I have taught you, the Brahmastra of this particular chapter. Now you can go and apply it anywhere. Let us say this is Cl, this is Cl, this is Cl. So what is the working of Cl? You all know about Cl. There is nothing. This is minus I dominant over positive M, but both of them will be failed. Only SIP works. Minus I only, minus I more than positive M, and minus I is very less. So the worst one will be the second. So the order of KB second. Then relatively good will be that. Okay, so the best will be the first. This is more minus I. Third is having more minus I, so it will become fourth, third, first. KB. Anyways, the last example of the day. Then we'll take a break. This is an aniline. This is aniline. This is aniline. This is aniline. Now this is NO2. This is NO2. NO2. No effect. This is showing minus M more than minus I. This is simply minus I. This is minus M more than minus I. But instead of everything, this matters the SIP. This doesn't work. SIP works. So SIP makes him the worst. Second is the worst. Which one is the best then? Fourth one is the best. So then first, then third, and then fourth. Check it out. Please try to solve the questions with me. These are very interesting questions, very much effective questions, and very much frequently asked questions. Okay, now better we solve some questions and then we'll wind up the session. Consider the basicity of following aromatic amine: aniline, para-nitroaniline, para-methoxyaniline. So it's very easy question. Let me try this question for you, and then rest of the question should be tried by your own. First is aniline. So guys, this is plus H more than plus I. This is plus M more than minus I. This is minus M more than minus I. And this is nothing. So what should we do? I think the best should be with nitro. So best is second, then first is good, then third is the worst actually, because third one is giving conjugation and it is providing you electron density which is not even required, which is no. Okay, worst हो गया. Anyways, this is directly proportional to the electron releasing group. So third is the best, then fourth, then first, and then worst will be the second, because all the electron density will be taken by nitro group. This is the answer of Kb. I was doing it with using Ka, but mistakenly made it. This is the correct answer, I think. Third, fourth, second. Third, fourth, first, second. Correct. So guys, try this question. Better you try by your own. Take your time. I'll be back in some time, and then I'll finish this lecture. Yeah guys, so anybody tried this question? Should I? This is simple aniline, nothing working. This is aromatic amine, and aromatic amines are always weaker because they are involved in the resonance, so that is why they are weaker. This is simply 1 degree amine, and this might be taking this as minus I effect only, then nothing else. Then here SIP will work, this will become definitely worst, and here this is amide, so this is partially going here and partially somewhere else. So now it's a big challenge. I think C should be the worst in the case of SIP, and the best test could be, the best is B. I find B is the best because in B there is no resonance involved, only 1 degree amine is there, and B, then followed by A, then C, and then D. This is a good question here. Let me check the correct answer. Okay, B is the correct. I told you this is the strongest base. B is the correct answer. So anyways, it was very much relatable, and there were so many clues here which were missing, but applying all concept all together, then only I got the correct answer. Try this question, very amazing one. So these two nitro groups definitely will not let easily do going for SIP. This is not just having the SIP effect, ortho effect, and one is the worst, third is the best. So I think third, second, first. Very simple. Next question. This question, try. Anybody want to try this question? So I have already explained the concept behind it. We have to check whether we are getting the more and more electron density. Electron releasing group should be there, and here I think these all are. This is a simple question actually. It seems like a very simple question. The first one is simple aniline. The first one and the second one, we are having one inductive effect. It will be showing. So plus I will work, and this is from two side. Plus I will work. I think the correct answer should be ZYX. C. Try this question. First is aniline, second will be SIP. So this will be the worst, and this will be the best. S is the best. S is the best. S is the best, followed by R, then P, and then Q. A is the correct answer. See how easy. Anyways, one more question and then we'll wind up. So probably the last question, everyone. OCH3 group. Okay, what does OCH3 do? OCH3 group has what? OCH3 group has the impact of positive M over minus I, but this is irrespective of any group will undergo SIP. So SIP, this will not work, only SIP will work. So this is the worst one. Then talking about this is minus I only work. This is plus M will work over minus I. So guys, this will be the best. This will make the best because it is giving the most electron density for nitrogen to attack our water molecule to acquire its S positive and releasing the OH minus. Now you suggest me the correct answer, everyone. S is the best. We know it. Followed by P, then R, and then Q. SPRQ. Okay, or maybe this could be also correct. SPQR, because after S, both of these cases are inductively working, and inductively it is destroying the basic strength. So that's it, everyone. We have plenty of questions with you. Try solving them. Be confident in them. There are so many questions I have come up with today. These number of questions will definitely help you to crack your JEE Mains and Advanced exam. I have given you enough of the theory. Whoever is watching this video, maybe today or tomorrow, you all will feel very comfortable after this 5-hour session that we have done something. Electronic effects, we know how to apply the electronic effects, and there are so many good questions I have come up with. So please try these questions, and that is it. Love you all. We'll connect tomorrow, day 3, GOC day 3, 4 o'clock. We'll connect. Everybody set a reminder. We'll literally come there and we'll find very amazing content on isomerism. I'll try to cover complete isomerism, structural plus stereo. So be there and we'll connect tomorrow. Bye bye. Take care.